Welcome back to Sleep Nova. Sit back, relax, and enjoy the show. In the beginning, there is nothing but darkness, an endless, silent void, and then a spark. I remember the darkness before light. I remember the quiet before the first dawn. In that primordial silence, the universe was newborn and starless. No sun, no stars, only a cold black expanse. But even in darkness there was the promise of light. The cosmos itself was pregnant with fire. And then it happened. Somewhere in the emptiness, gravity drew wisps of hydrogen gas together into a tight knot until, at last, ignition. A newborn star flared into existence, the first sunrise in the cosmos. Its light spilled out, pushing back the cosmic night. And it was not the last. Soon another star lit, and another, thousands, and then millions. The long dark ages of the young universe yielded to a spreading dawn of starlight. Tiny galaxies assembled and filled with brilliant, massive suns. The cosmos experienced its first morning. Eons later, in one quiet corner of that cosmos, I was born. I, the sun, came into being amid the leftovers of earlier stars. In a spiral arm of the Milky Way galaxy, a great cloud of gas and dust began to collapse under its own gravity. Perhaps the shockwave of a distant supernova, the death cry of an ancient star, rattled that cloud and started it clumping. Deep at its center, matter gathered and compressed. As a baby, I was cocooned in that dark nebula, growing denser and hotter. My birth was violent and inevitable. Gravity crushed me tighter and tighter until my core blazed at millions of degrees. In that moment, starlight erupted from within me. I became a star. The darkness inside the nebula was torn apart by my radiance. I blew away the remaining fog of my birth cloud, claiming my place in the galaxy's family of suns. Light spilled out across newly formed worlds that circled me. For the first time, dawn bathed the faces of those infant planets. On one of those worlds, a little blue planet called Earth, there came a morning that no being yet witnessed. The young Earth turned under my newborn light, its surface still molten in places from recent creation. When it cooled and formed oceans, each day my warmth stirred the winds and waves. The first sunrise on Earth may have had no eyes to see it, but it was the beginning of something profound. In my golden glow, the stage was set for life to one day emerge. Day after day, as that world spun, my light chased shadows across its surface. I marked the passage of time with each sunrise and sunset, even before any living thing was there to name them. Ages passed. Life arose in the seas of Earth, tiny, humble cells that danced in my light. And eventually, life grew clever and climbed onto the lands and looked up at me in awe. Imagine the first people, shivering through a long, cold night, watching the eastern sky brighten with my approach. To them, that was a miracle beyond understanding. Darkness giving way to light. Is it any wonder they began to revere me? When human eyes first opened, they opened to sunlight. When human hearts first felt wonder, it was at my radiant dawn breaking the horizon. They felt my warmth on their skin and knew that I gave life, that I banished the terrors of the night. So they gave me names and stories. In their yearning to understand, they made me a god. I remember those stories, for I have watched humanity tell them for millennia. They called me by countless names, wove countless myths around me. To the ancient Egyptians, I was Ra, the great sun god, sailing across the sky each day in a golden bark. They imagined me as a majestic king in a solar boat, voyaging through the sky from sunrise to sunset. And each night, they said, I descended into the underworld to battle the serpent of chaos, Apophis, a monstrous snake bent on devouring me and bringing eternal night. Every dawn was a victory as I, Ra, emerged triumphant, reborn with the morning light. The Egyptians built temples aligned to the sun, obelisks and pyramids that caught my rays at dawn and dusk. They believed their pharaoh was the son of Ra, a living embodiment of the sun on earth. Each sunrise, priests sang hymns to celebrate my return from darkness. They told of how I, in the form of a scarab beetle Khepri, rolled the sun across the sky like a glowing dung ball, and how at dusk I became Atom, the aged sun setting, only to be reborn again. My daily cycle was the very heartbeat of their world, the promise that light overcomes darkness. Far to the east, on the Indian subcontinent, I was worshipped as Surya, divine sun, riding a splendid chariot. In Vedic hymns, they praised me as the eye of the universe, the soul of all existence. They said my chariot was drawn by 7 immortal horses, representing the 7 colors of light or the 7 days of the week. With the dawn, the red glow of Ushas, the dawn goddess, heralded my arrival, and then Surya's chariot would surge across the heavens, pulled by those 7 radiant horses and driven by Aruna, the charioteer of the dawn. Each day, I rode across the sky, pouring out light and life. The ancient poets of the Vedas wrote beautiful verses to me, begging for my blessing. O Surya, remover of darkness, controller of time, may we see 100 autumns under your benevolent gaze. At sunset, they imagined, I traveled beyond the horizon to illuminate the other side of the world. In their salutations and yoga practices, they faced me at dawn with folded hands. Surya Namaskar, the sun salutation, honoring me as the source of energy. They even reckoned time by me. One ancient Indian text muses that for the gods, a year is but a single day for the sun, and I am timeless witness to all. Across the ocean in the Americas, great civilizations also turned their eyes to me. The Maya revered me as Kinich Ahau, the Sun Lord. They carved my image as a majestic, bejeweled figure with an aquiline nose and square eyes, often depicted with jaguar traits. To them, I was so powerful that each evening I transformed. When I reached the western horizon and sank, the Maya believed I became a fearsome jaguar prowling through the dangerous darkness of the underworld, Xibalba, fighting off demons until I could rise again. At dawn, I would return from that night journey, once more a young man of light. The cycle of day and night was a sacred drama. The Maya built their cities to track my motion. At certain temples, the sunlight on equinox or solstice would align perfectly through doorways or cast the shadow of a serpent along pyramid steps. On the pyramid of Kukulkan at Chichen Itza, every equinox my setting rays create the illusion of a serpent of light slithering down the stairs, a sign to them that I sanctioned the turning of the seasons. They read their calendars and planned plantings and harvests by my yearly cycle. Mayan rulers took on my mantle too. Some styled themselves as the embodiment of the sun on earth, claiming my divine right to rule. I was their guide and their giver, the one who made the maize grow and the days turn. In truth, there is scarcely a culture on earth that didn't recognize my power with reverence or fear. The Inca called me Inti, and their emperor was the child of Inti, claiming descent from me. They built Coricancha, the temple of the sun in Cusco, where my rays at summer solstice would reflect brilliantly off walls lined with gold. To appease me, they offered lavish gifts and sacrifices, even life itself, believing that if I was not fed, I might hide my face and leave them in cold darkness. On the other side of the world, the ancient Chinese told how in primordial times there were 10 suns, 10 fiery birds that took turns carrying the sun across the sky each day. One day, all 10 appeared at once, scorching the earth with unbearable heat, until the archer Hao Yi shot down 9 of them with his bow, leaving only one sun, me, to rise and set. To this day, Chinese New Year celebrations honor me with firecrackers and dragon dances to encourage my return after the dark of winter. In Japan, I was revered as Amaterasu, the great solar goddess, ancestress of emperors. They say, Once I grew upset at my brother's mischief and hid myself in a cave, plunging the world into darkness. The other gods grew desperate. Without me, crops failed and evil spirits ran free. So they lured me out by staging a raucous dance and holding up a mirror at the cave entrance. Curious at the laughter, I peeked out, saw my brilliant reflection and paused, allowing the strong deity, Ame no Tajikarawo, to pull me from the cave. Light was restored to the world, and the door of the cave was sealed so I could never hide forever again. The Japanese built the Great Eyes Shrine in my honor, renewing it every 20 years to keep it eternally young, much as each sunrise renews the day. Through these myths, humanity gave me many faces. I have been a benevolent creator and a wrathful destroyer, a male god and a female goddess, a feathered serpent, a golden disc, a divine eye watching over all. I have been worshipped on mountaintops at dawn and implored during eclipses when I briefly hide my face behind the moon. To early humans, an eclipse, when day suddenly turns to eerie twilight and my halo, the corona, gleams around a black disc, must have been terrifying. A moment when they feared the serpent or dragon was devouring me. They banged drums, clanged pots, prayed fervently for my return. And when I emerged again, the relief and jubilation spoke to just how deeply they depended on my light. They built monuments to chase me across the sky. Great stone circles like Stonehenge in England were carefully aligned with my movements. On the summer solstice, the longest day, the rising sun shines directly through its heelstone to the center of the circle. On that day, thousands of years ago, ancient peoples gathered there at dawn, watching the first rays shoot through the stones, confirming that the wheel of the seasons had turned and long days of warmth were upon them. In Ireland, at Newgrange, a tomb older than the pyramids, they engineered a narrow roof box above the entrance, just so that on the winter solstice sunrise, a beam of my light would pierce the dark passage and illuminate the central chamber. Imagine standing in that cold stone room on the darkest day of the year, after the longest night, and seeing a single shaft of sunlight creep in, a golden finger extending slowly along the ground and up the wall, flooding the chamber with radiance. To those Neolithic farmers, it must have been magical. Proof that even in the dead of winter, I had not abandoned them, that light would return and life would continue. Year after year, they repeated this ritual, tracking my yearly dance with the earth. I was their monarch in the sky, a heavenly king to which all things paid homage. They crowned their kings and queens in gold to evoke my rays, set gleaming sun discs atop their headdresses. The idea of a halo around the head of a holy person is nothing more than a mimicry of my divine glow. In many languages, the word for sun became synonymous with king or eye of God. They built cathedrals that flooded with colored light when my rays shone through stained glass windows, trying to capture a fragment of my glory in their places of worship. How many prayers, how many poems, how many songs through the ages have been offered up to me at sunrise? Too many to count. I warmed the bones and hearts of humanity for tens of thousands of years, and they returned my gifts with devotion and awe. Yet for all the love and fear they held for me, humanity did not truly know me. I kept my true nature secret, hidden behind a blinding glare. To their eyes, I was a bright disk that crossed the sky predictably, but the details of what I was, what I truly am, eluded them. Some thought me a benevolent deity riding a chariot, others a fiery eye or a jewel hung in the firmament by the Creator. It is only in relatively recent times that humans, with curious minds and persistent observation, peeled back the veil of myth to see me for what I am, not a god, but a star, a colossal, natural engine, governed by the laws of physics rather than the whims of gods. The journey to that understanding was long and fraught. For centuries, thinkers pondered what I was made of, and how I could possibly burn so steadily. On Earth, a bonfire dies out in hours. An oil lamp sputters and fades when fuel is spent. Yet, I have blazed for billions of years with undiminished vigor. What fuel could feed a fire for so long? Some speculated I was a burning coal of some unknown kind, or a ball of molten iron. In the 19th century, scientists guessed that I might shine by gravitational contraction, slowly shrinking and heating up, converting gravitational energy into light. But even that could only sustain me for tens of millions of years. And by then, geologists and biologists had evidence Earth was far older. I remained an enigma. The ancient cultures had named me well as a mystery and a miracle, because no ordinary fire or combustion known could explain my endurance. Then, in the early 20th century, human knowledge unlocked the atom, and with it came the revelation that finally unraveled my secret. I am no mere fire, I am a nuclear furnace. Inside me, atoms fuse together, releasing energy according to the famous equation E equals mc2. In my core, the very building blocks of matter are transmuted. Mass is converted to energy, and that energy is what you see as sunlight. In realizing this, humanity redefined me not as a supernatural chariot or an eye of a god, but as a machine of nature, a self-sustaining reactor forged by gravity and quantum forces. They discovered that I, the sun, am actually a fairly ordinary example of a star, the same kind that dots the night sky. So here I am, a star. One among countless others, but unique in being yours. I sit in the center of the solar system, a massive glowing sphere of hot plasma, holding 9 planets, if one counts even the far-flung dwarf Pluto, and myriad asteroids and comets in my gravitational embrace. I am over 1.3 million times the volume of the Earth. About 109 Earths could be lined up across my face. More than 99.8% of all the mass in the entire solar system is me. In a very real sense, I am the solar system. The planets are just a tiny fraction of leftovers. My gravity commands them. It is the invisible leash that keeps Earth and its neighbors orbiting year after year. In the days of old, humans truly were right to picture me as a monarch and the planets as my court. I wear a brilliant corona like a crown, and each planet circles like a dutiful subject, receiving light and warmth at my pleasure. I am the anchor of this system. Without me, the planets would drift into the void, cold and alone. It is my gravity that binds them together in a family, and my light that makes Earth a living world rather than an ice-coated rock. Yet, humbling as it might be, I am but one star among billions. If you step back and look at the Milky Way galaxy on a clear night, every tiny star you see sparkling is a sun in its own right, perhaps with its own planets and stories. From afar, I would appear just like one of those pinpoints of light. There is nothing particularly conspicuous about me to an outside observer. I'm not the brightest star in the galaxy, nor the biggest, nor the most active. I'm a fairly typical yellow dwarf star, spectral type G2V if you use human classifications. In the grand tableau of the cosmos, I blend in among the crowds. In fact, the majority of my stellar siblings in the Milky Way are smaller and cooler than I, the red dwarfs. But there are also many that outshine me thousands of times over. Still, to you, I am special. I am your sun, the only one you have ever known. While other stars speckle the night, out of reach, I dominate your day and sustain your life. For Earth's creatures, I am the only sun that matters. In that sense, I am both ordinary and extraordinary, an average star doing an average star's job, but uniquely precious to you because I cradle your world. Think of it. On the cosmic scale, I'm a mere mote, but from your perspective, I am everything. This paradox has dawned on humanity slowly. Ancient astronomers once thought Earth was the center of all things, and that I revolved around you. It took the genius of Copernicus, Galileo's observations of my sunspots, and Kepler's calculations of planetary orbits to reveal the truth. It is Earth that orbits me. I am the hub of your world's motion, the heart of the solar system. Year by year, Earth completes a grand orbit around my throne. Day by day, it spins on its axis, facing me and then turning away, causing the cycles of day and night that regulate all life's rhythms. Once humanity accepted that I was the center of their system, not Earth, it was a profound shift. You realized your world is not the monarch of creation, but a satellite of the sun. And beyond me lie stars beyond stars, implying, perhaps, that even I orbit something greater. Indeed, I do. I circle the center of the galaxy every 230 million years along with my stellar kin, bound in a vast spiral structure of the Milky Way. On a dark night, far from city lights, when you gaze up at the Milky Way's cloudy band, you are seeing the combined glow of billions of distant suns. Among them somewhere is our sun, though you cannot pick it out with your eyes. If some distant astronomer on a planet orbiting another star were to look toward this region of space, they would see our sun as a modest star in the constellation we call Cassiopeia. To them, it might not stand out, but for us here, it is everything. It is daylight and warmth and gravity and time. So what exactly is a star, truly? Let me tell you the story of a star's life, for it is my story too. A star begins in darkness, fittingly. Deep in a cold molecular cloud of gas and dust, some trigger, perhaps the passage of a spiral arm shock or the blast of a distant supernova, causes a clump to form and start collapsing under gravity. As it collapses, it spins and flattens into a whirling disk. At the center, matter piles higher and higher, density and pressure climbing. The core grows hotter, first thousands, then millions of degrees. For a long while, the protostar is dark to the outside universe, hidden in its dusty womb, though it glows dimly in infrared. Gas from the infalling cloud rains down, accelerating and heating the nascent star further. When the core temperature crosses about 10 million degrees Celsius, a moment of transformation occurs. Hydrogen fusion begins. 4 hydrogen nuclei start fusing into one helium nucleus, and in that process, a tiny fraction of their mass is converted into a tremendous burst of energy. This is the spark of true starlight. The protostar becomes a real star. Pressure from the fusion fire inflates it, and the collapse slows. A delicate balance is reached. The inward pull of gravity is matched by the outward push of hot gas pressure from the core. In that balance, that hydrostatic equilibrium, a star finds stability and enters the long, calm phase of its life, known as the main sequence. I have been in this phase for over 4.5 billion years, and I will remain so for about 5 billion more. All that time, I steadily convert hydrogen to helium in my center, shining steadily. Picture, if you will, the interior of a star like me. From the outside, my shining face, the photosphere, looks tranquil, but beneath is a layered structure. At the core, extending about a quarter of the way out from center, is where the temperature and pressure are high enough for fusion. There, hydrogen nuclei, protons, slam together in a multi-step process called the proton-proton chain, ultimately forming helium and releasing energy. The conditions are extreme, about 15 million degrees Celsius, and over 200 billion times the atmospheric pressure at Earth's surface. It is a cauldron, a crucible where matter is in an exotic plasma state, and quantum tunneling allows protons to overcome their repulsion and fuse. Every single second, my core fuses roughly 600 million tons of hydrogen into 596 million tons of helium. The missing 4 million tons, that mass is converted into pure energy, gamma-ray photons and neutrinos, according to E equals mc2. 4 million tons of mass, gone in a flash, every second of every day. This is the power that drives the sun. To put it another way, I lose mass by shining. With each heartbeat of fusion, I very slowly shed weight, radiating it away as the light and heat that bathes the solar system. 4 million tons per second may sound staggering, and it is, yet it's only a tiny fraction of my total mass. Even at this prodigious rate, I can keep shining for billions of years before significant depletion. Think of my core as a furnace, an alchemical furnace where elements transmute. It is also my heart, where my energy is born. The energy released in the core keeps the furnace hot, and that heat pushes outward, exactly countering the inexorable inward crush of gravity. This dynamic piece, pressure outward, gravity inward, is what keeps me round and stable, neither collapsing nor exploding. I live in balance, a shining harmony of forces. In this way, a star is like a living thing, maintaining homeostasis. If the core produces a bit too much energy, it expands and cools slightly, slowing the fusion. If it produces too little, gravity compresses it more, heating it up and boosting fusion. A self-regulating sphere of plasma. Astonishing, no? It is as if I have an internal thermostat with gravity's firm hand on the dial. Through this balance, I have shone with a fairly steady brightness for a very long time, providing a consistent environment that allowed life to flourish on Earth. Let us journey with a photon of light created in my core. It begins as a gamma ray, an extremely energetic packet of electromagnetic energy, born from one of those fusion reactions. Perhaps when two hydrogen nuclei fused into deuterium, or when a positron met an electron and annihilated, yielding pure photon energy. This newborn photon is in a crowded, chaotic place. The core is so dense, imagine the density of lead, or even heavier, that the photon can travel only a tiny fraction of a millimeter before it slams into a particle, likely an electron or ion, and is absorbed or scattered in a new direction. Thus begins a long, random walk outward. The photon's energy may be absorbed and re-emitted at lower energy, or split into multiple lower energy photons, as it pinballs its way through the dense core and then the radiative zone that surrounds the core. It ricochets countless times, zigzagging outward, losing a bit of energy at each interaction. What started as a blistering gamma ray gradually becomes X-rays, then ultraviolet, and eventually visible light by the time it nears the surface. The journey is unbelievably slow. Trapped in the stellar interior, a photon takes an incredibly long time to get out. By some estimates, it can wander on the order of tens of thousands, even up to 1 million years inside me, before finally escaping. That means much of the sunlight that greets your eyes today could have been generated when early humans were first learning to make tools, or even when Neanderthals walked the earth, or earlier still. In a very real sense, sunlight is ancient by the time it reaches you, born long ago in the furnace of my core, and only now completing its long journey to the surface. Eventually, after perhaps hundreds of thousands of random bounces, our photon friend reaches my outer layers. The density has dropped enough that the photon can finally break free into space. It emerges from my visible surface, the photosphere, as part of the warm glow you recognize as sunlight. Now its journey is swift and straight. Once free of me, it zips through the vacuum of space at the ultimate speed, the speed of light, 300,000 kilometers per second. In a mere 8 minutes and 20 seconds, a photon crosses the 150 million kilometers from my surface to Earth. Every sunrise then is in a sense the culmination of a story that started deep in my core long before any human ever saw the sky. The light that blushes the sky, pink and orange at dawn, left my surface just minutes ago, but it was born in my heart ages in the past. When you feel the warmth of the morning sun on your face, you are touching something that was brewed in a star's core in prehistoric times and has traveled across space to brighten your day. Think about this. If I were to suddenly extinguish my core this instant, you would not know it on Earth for over 8 minutes. The sunlight already on its way would still arrive, and only after those minutes would darkness fall. Even then, the sky might still glow faintly for a while, with residual light scattered in the atmosphere. But eventually, night would reign, and a dreadful cold would descend, ending life as you know it. Fortunately for you, I have no intention of going out anytime soon. My nuclear hearth is well stocked for eons ahead. So the sunlight that bathes your world is not a single hue, but a spectrum of many colors and energies. What appears to your eyes as gold and white light is in fact a rich blend of all the colors of the rainbow and beyond. If you pass my light through a prism, it fans out into reds, oranges, yellows, greens, blues, indigos, violets, a glorious spectrum. But that visible band is only a small portion of my full emanation. I shine most strongly in visible light. That's why your eyes evolved to see those wavelengths. But I also emit invisible light on either side of the visible range. Just beyond the violet end lies ultraviolet, a more energetic radiation that you cannot see, but whose effects you know. It causes sunburn on your skin after long exposure, and it stirs the chemistry of life. High in Earth's atmosphere, my ultraviolet rays split oxygen molecules and create the protective ozone layer which shields the surface from the most harmful UV. Without ozone, that harsh ultraviolet would sterilize the land. At the other end, beyond visible red, lies infrared light, essentially heat radiation. You feel it as warmth on your skin. On a sunny day, the comforting heat that seeps into your bones is my infrared emissary. Even when you stand in shade, you feel warmth radiating from sun-heated surfaces, an echo of my gift. But the spectrum extends further. I produce some X-rays as well, particularly during flares. Sudden eruptions on my surface can unleash bursts of X-rays that momentarily ionize Earth's upper atmosphere and disturb radio communications. I also whisper in the low-energy radio part of the spectrum. My corona, the outer atmosphere, emits radio waves that your instruments can detect, and sometimes, during solar storms, the radio output roars. So from the highest energies, X-rays, extreme UV, to the gentle long waves of radio, I span a broad orchestra of light. And then, beyond electromagnetic radiation, I send out particles. A constant stream of matter flows from me, called the solar wind. My outer corona is so hot, millions of degrees, that it cannot be contained by gravity. It expands outward in all directions, a ceaseless outflow of electrons, protons, and helium nuclei, peppered occasionally with heavier ions. This solar wind is like a breath, an exhalation that fills the solar system. It blows past all the planets, carving out a vast bubble in the galaxy, called the heliosphere. At Earth's orbit, the solar wind is a tenuous gust, only a few particles per cubic centimeter, racing by at about 400 kilometers per second, nearly 1 million miles per hour. You would never feel it directly, but it's there, shaping Earth's magnetic environment. The wind carries embedded magnetic fields from me, linking planet and star in an electromagnetic embrace. Every second, I lose millions of tons of material in this wind. It's a slow peeling away of me, though trivial compared to my mass. Still, over billions of years, it has subtly altered planetary atmospheres. For instance, likely stripping much of Mars's air long ago. Among the invisible travelers from me, perhaps the most ghostly are neutrinos. These ethereal subatomic particles are born directly from the fusion reactions in my core. Unlike photons, neutrinos barely interact with matter. They slip through the dense solar interior almost as if it weren't there, and stream out into space at nearly the speed of light. Trillions of neutrinos fly outward in all directions, passing through planets, rocks, and living bodies with ease. Right now, as you hear these words, about 65 billion neutrinos per second are passing through each square centimeter of your body, mostly from me. Yet you feel nothing. Neutrinos hardly ever collide with atoms. They are my silent messengers, carrying away about 2% of the energy from each fusion reaction. For a long time, humans built giant detectors deep underground, trying to catch just a few of these elusive particles from the sun. For decades in the 20th century, those experiments found only about 1/3 the neutrinos they expected, puzzling scientists. Was something wrong with their understanding of my core? Eventually, they solved the riddle. Neutrinos were changing identity, or flavor, en route, a subtle quantum effect. Once that was accounted for, the missing neutrinos were found, confirming that indeed the fusion fires in my heart burn exactly as theory predicts. Imagine, humans confirmed the reactions in my core by catching a handful of ghostly particles that had traveled straight out from my center, through 150 million km of space and a kilometer of rock, to flash faintly in a vat of fluid. It is a testament to how far they've come in grasping my true nature. Thus, I shine on you not just with soothing visible light, but also with invisible ultraviolet that tans and burns, with infrared that warms, with X-rays and radio waves and a wind of charged particles and a shower of neutrinos. My light is a spectrum, a symphony of frequencies. Some parts of it you perceive directly, others you only discovered with ingenious instruments. But altogether, this sunlight sustains your world. However, I am not a completely placid giver of light. I have my moods and cycles, and sometimes, I must confess, I rage. If you watch my surface, as you now can with telescopes and satellites, you'll see that it is far from uniform. It seethes and boils like a pot of oatmeal. My visible surface is covered with granules, convective cells of rising and falling gas about the size of Texas or a large European country each, giving my face a textured, grainy appearance up close. These granules are the tops of columns of hot plasma that well up from the interior, cool at the surface, and sink down along dark lanes. I look like a gigantic boiling ocean of fire, each bubble a continent wide and lasting only minutes before dissipating. But beyond that ever-present boiling, there are larger, more dramatic features. Dark sunspots sometimes dot my face, often in groups, forming and dissolving over days or weeks. These are regions of intense magnetic field, where the surface is cooler, about 4,000 K, than surrounding areas, about 5,800 K, so they appear dark by contrast. To human eyes, they might look like small blemishes, but don't be fooled. A typical sunspot is larger than the Earth, a colossal magnetic storm on my surface. In truth, they are like wounds on my shining body, dark, temporary lesions, where my concentrated magnetism suppresses the boiling and leaks out through the surface. Around the edges of these spots, bright faculae often appear, areas where magnetism locally heats the surface. Sunspots can endure for days or weeks, then fragment and dissipate as the magnetic field reconfigures. They are not random, they follow a cycle. Every approximately 11 years, I go through a rhythmic dance of activity known as the solar cycle. At the beginning of a cycle, solar minimum, I may have few or no sunspots at all. My face is relatively unmarked. As the cycle progresses, sunspots begin to emerge, first at mid-latitudes, around 30 degrees north or south of my equator. They tend to come in bipolar pairs, linked by loops of magnetic field arching out of the surface. As months and years pass, more spots appear, often in greater numbers and closer to my equator as the cycle advances. The number of spots climbs toward a peak, solar maximum, when dozens of sunspots can dot my visage at once, and tremendous magnetic energy is stored in my atmosphere. Then, after the peak, activity declines again, spots becoming fewer, until a few years later, another quiet minimum arrives. Then a new cycle begins. Interestingly, with each new cycle, the polarity of my magnetic field flips. The north magnetic pole and south magnetic pole swap places. So in truth, the full magnetic cycle is about 22 years, 2 sunspot cycles, for my polarity to return to original orientation. At solar maximum, not only are spots numerous, but they spawn solar flares and eruptions more frequently. It's as if my heartbeat quickens and I become feverish with storms. What causes this mysterious cycle? It is my magnetic dynamo at work. The churning of electrically conductive plasma in my interior generates a magnetic field, and my rotation tangles and stretches that field. Here's an image. I rotate faster at the equator, about 1 rotation in 25 Earth days, than at the poles, which take about 35 Earth days per rotation. This differential rotation winds up my magnetic field lines like a twisted rubber band. Over about a decade, the field becomes highly stressed and contorted. Loops of magnetism burst through the surface, bringing those cooler sunspots with them at their foot points. Eventually, the field becomes so twisted it partially cancels and reconfigures itself, flipping polarity. The cycle then starts anew with fresh polarity. Humans have tracked this cycle for centuries. The sunspot counts carefully recorded since the days of Galileo and Scheiner in the 17th century show this rising and falling pattern. At times, it falters. There was a period from roughly 1645 to 1715, known as the Maunder minimum, when hardly any sunspots were seen at all. During that time, historically, winters in Europe were bitterly cold and prolonged. The Thames River froze, and glaciers advanced, part of the Little Ice Age. A quieter sun may have contributed to those colder climates. Even though my brightness changes only a fraction of a percent over the cycle, apparently even small variations can have noticeable effects on Earth's climate in certain circumstances. Conversely, during the 20th century, I had some of the most active cycles ever recorded, like the mid-20th century peaks. Though nowadays scientists note that my recent cycles have been a bit weaker than those mid-century ones. Still, the cycle continues inexorably. In each cycle's dawn, new sunspots appear at higher latitudes. Then as years pass, they form closer to the equator, drifting sunward as if drawn to an unseen gravity at my middle. This pattern, when graphed over time, makes a shape like butterfly wings, a beautiful order underlying my seeming chaos. Sunspots are visible signs of the titanic magnetic forces roiling within me, and those forces occasionally snap. When they do, storms erupt from my surface and atmosphere, hurling energy and matter into space. These are the moments when my benign visage turns violent. I am generally a nurturing star, but I have my outbursts. Star and myth, god and machine. I am also occasionally a dragon breathing fire. Consider a solar flare. In an active region around sunspots, magnetic field lines can become twisted and braided. If they suddenly realign, imagine a tangled rope that abruptly untangles itself. The energy stored in the magnetic field is explosively released. In seconds to minutes, I accelerate particles to near light speed and heat local gases to tens of millions of degrees, emitting a burst of X-rays, gamma rays, and energetic protons. A flare is a flash of brilliance, often visible as a sudden brightening in ultraviolet or X-ray images of the sun. From Earth, you might not see much invisible light. Flares can cause a slight increase or a white light flare, rarely. But spaceborne detectors register the intense high-energy photons. If Earth is along the line of fire, these X-rays reach it in just 8 minutes, like normal sunlight. They ionize the upper atmosphere, potentially disrupting radio communications and GPS signals by creating sudden ionospheric disturbances. Even more dramatic are coronal mass ejections, CMEs. These are massive belches of plasma from my corona, often associated with flares or eruptive disturbances around sunspot groups. A CME is like a billowing cloud of charged particles and magnetic field that I hurl into space. It can contain billions of tons of material, actual fragments of my corona, moving at speeds of 1 million or more kilometers per hour. Imagine an enormous, expanding bubble of electrified gas, many times larger than Earth, racing outward. If one of these is aimed at Earth, a collision is on the way in a day or two. Earth has warning only via satellites that see the eruption, and then perhaps 1836 hours before impact. When that CME slams into Earth's magnetic field, it's like a shockwave hitting a protective shield. The Earth's magnetosphere shakes and shudders under the assault. Charged particles rain down the field lines toward the magnetic poles. When my storms reach your planet, beautiful and terrible things can happen. The beautiful, auroras, the northern and southern lights. Those charged particles, guided by Earth's magnetic field, spiral into the upper atmosphere near the polar regions and excite atoms of oxygen and nitrogen, making them glow. Curtains of green and red light ripple across the polar skies, dancing and shimmering. It is as if the sky itself is remembering the cosmic battle between sun and darkness, painting it in ethereal hues. Auroras are my delicate fingerprints, the lovely side of space weather. But the terrible, those same electric currents induced in Earth's magnetosphere can wreak havoc on your technology. In 1859, a mighty solar storm, now known as the Carrington event, blasted Earth. Auroras were seen as far south as the Caribbean. The skies over the eastern US turned so crimson at night that people thought a great fire was burning on the horizon. Telegraph systems, the high tech of that era, went haywire. Sparks flew from telegraph lines and equipment. Some offices caught fire. Operators received shocks. The nascent electrical infrastructure was overwhelmed by induced currents. If a storm of that magnitude hit today, with our enormous network of power grids, satellites and communications, the damage could be severe. Even lesser storms have caused trouble. In 1989, a strong CME impact induced currents that knocked out the power grid in Quebec, plunging millions into darkness for hours on a cold March night. Satellites have been blinded or lost due to solar energetic particles blasting their electronics. Astronauts on spacewalks or en route to the moon would be in grave danger from the radiation of a major solar event. They would need to seek shelter behind shielding quickly. Thus, while I generously sustain life, I can also, in my more tempestuous moments, disrupt the modern systems that life has built. This realization has given rise to the field of space weather, forecasting my moods much as meteorologists forecast terrestrial storms. Scientists keep a constant watch on me with satellites stationed 1 million miles sunward of Earth at a point called L1 to give early warning of incoming solar winds and shocks. They monitor my sunspots and magnetic regions, trying to predict when a flare or CME might erupt and how strong it might be. Your species has learned that my storms are not merely curiosities. They directly affect airline routes. Planes sometimes avoid high latitudes during solar storms to reduce radiation exposure. Satellite operations, even the accuracy of navigation systems. From my perspective, these flares and eruptions are just a way to release pent-up energy and stress, a bit like the sun stretching its magnetic limbs and occasionally cracking a knuckle. I do not aim them in malice. They occur as a consequence of my magnetic dynamics. Earth just sometimes happens to be in the line of fire. Other planets too feel my wrath. I've sandblasted Mars's atmosphere over eons, and I induce auroras even on Jupiter and Saturn. Their strong magnetic fields light up near their poles under my charged particle rain. I send my love and fury across the whole solar system. Yet for Earth, I remain overwhelmingly a life giver. Life and the sun are inseparable. From the tiniest microbe to the tallest tree, almost every organism ultimately draws energy from my light. Long ago, some clever bacteria evolved a way to harness sunlight directly, photosynthesis, using my photons to turn carbon dioxide and water into sugars and oxygen. That was a pivotal moment in Earth's history. With that, plants and cyanobacteria in the oceans began transforming the atmosphere, filling it with oxygen, a waste product for them, but a boon for complex life that would follow. Over billions of years, my light has literally fed life and shaped the biosphere. Every leaf is a solar panel, converting my light into chemical energy. Every fruit, every stalk of wheat, every blade of grass is essentially stored sunshine, waiting to be consumed by an animal or human to provide energy. Even the fossil fuels you dig up, coal, oil, natural gas, are ancient sunlight, trapped by photosynthetic organisms millions of years ago, buried and transformed. When you burn a log in a campfire or gasoline in an engine, you are releasing sunlight captured long before humans existed. Think of the sprawling forests, each tree spreading green leaves toward the sky, drinking in my rays to create wood and fruit. Think of the phytoplankton blooming in sunlit surface waters of the ocean, forming the foundation of marine food webs. Without me, the great chain of life's nourishment would snap. Only a few special ecosystems like deep-sea hydrothermal vent communities live without sunlight, relying on Earth's internal heat. But they are rare oases. The vast majority of life on Earth depends on me directly or indirectly. I drive the photosynthesis that provides food and oxygen. I also drive the climate and weather that distribute water and nutrients. My warmth keeps Earth's water liquid. Were Earth much farther away, its oceans would freeze solid. Much closer, they would boil off. Your planet sits in the Goldilocks zone, not too hot, not too cold, at just the right distance for liquid water and life as you know it. This is no coincidence. Life adapted to the conditions present, and Earth's position was crucial. Over Earth's history, my output has not been absolutely constant. I have been slowly brightening. When Earth was young, billions of years ago, I was dimmer, about 70% of my current luminosity. Paradoxically, the young Earth still had liquid oceans, a puzzle known as the faint young sun paradox. It appears Earth's atmosphere had a thicker blanket of greenhouse gases, carbon dioxide, methane, back then, trapping heat to compensate for my youthfully lower power. As I brightened over time, Earth systems, perhaps aided by life's influence drawing down CO2, adjusted to prevent a runaway warming. Life and geology danced in tune with my gradual change, maintaining a habitable balance. On shorter timescales, my 11-year cycle can make a small difference, fraction of a percent, in total radiation. While not hugely influential on climate compared to human-caused changes today, there is evidence that extended periods of low solar activity, like the Maunder minimum, had modest cooling effects regionally, especially in the northern hemisphere. Conversely, periods of high activity might have given slight warming. But even during the Little Ice Age, my role was one factor among volcanic eruptions and ocean circulation changes. Nonetheless, human civilizations noticed patterns. Medieval scholars spoke of a wine harvest that correlated with sunspot cycles. Modern scientists correlate small variations in stratospheric winds and maybe rainfall patterns to the solar cycle. My UV output varies more significantly, a few percent with the cycle, affecting ozone chemistry and atmospheric heating at high altitudes, which can have subtle trickle-down effects on weather. The details are complex, but one thing is clear. Over millennia, your climate and my fluctuations have been entwined in subtle ways. For example, some researchers suspect that the dearth of sunspots in the Maunder minimum helped trigger or exacerbate winters so cold that fairs were held on frozen rivers. On the flip side, a slightly more active sun in the mid-20th century perhaps gave a tiny boost to the warming at that time, though dwarfed by greenhouse gas effects. Beyond climate, I have marked time itself for humanity. The very concept of a day is tied to one rotation of Earth under my light. The concept of a year is one orbit around me. Early humans noticed the cyclic lengthening and shortening of days, the march of seasons as the sun's path across the sky rose and fell over the year. They built calendars, solar calendars, to track planting and harvesting seasons. Monuments like Stonehenge, Newgrange, and countless others across cultures were not only spiritual, but also practical, serving as giant calendars to mark solstices and equinoxes. The Egyptians, for instance, noticed that the annual heliacal rising of Sirius, a bright star, just before dawn, coincided with the Nile flood, and fixed their calendar to the sun to predict seasons. But they also built temples where on the solstices or the pharaoh's birthday, the morning sun would illuminate the innermost sanctum, a spectacular alignment celebrating cosmic order. The concept of months originally came from the moon's cycle, but solar calendars eventually dominated because agriculture demanded alignment with the solar year's seasons. Every morning, the roosters crow, the opening of flowers, the human sleep-wake cycle, all are tuned to my rising. Circadian rhythms in most living beings are essentially internal clocks set by my schedule of light and dark. You structure your days around sunrise, noon, sunset, even if artificial light now stretches waking hours. In the far north, where winter brings very little sun, humans long for my return. Festivals of light dot midwinter, from Yule to Diwali, echoing ancient solstice celebrations that welcomed the return of longer days after the darkest point of the year. The very words morning and tomorrow carry the expectation of my reappearance. Throughout history, kings and commoners alike have been enthralled by eclipses and comets crossing my domain. Ancient Chinese records meticulously recount solar eclipses, and woe to the royal astronomers if they failed to predict one. It was seen as a breakdown of harmony between heaven, the sun, and earth, the emperor's domain. The Babylonian priests learned to predict eclipses, the Saros cycle, and used that as political power. Ancient Greek philosophers like Anaxagoras dared to say, "I was not a god, but a fiery stone," for which he was punished, showing how radical it was to demystify me. Even Copernicus and Galileo, when they unveiled that Earth orbited the sun, faced resistance because it demoted Earth from the center and upset theological ideas. I have always held a central place not just in the sky, but in the human psyche and society. Consider how many idioms and metaphors involve me. Sunrise industries for new ventures, a ray of sunshine for a happy person, under the sun, meaning anywhere in the world, make hay while the sun shines, urging one to act while conditions are favorable. I have been the ultimate symbol of positivity, certainty, and inevitability. The sun will rise tomorrow, a phrase to indicate hope and continuity. Even your modern physics speaks of a sunny day scenario for simplicity in calculations. I permeate your language and thought at every level. My influence extends to the calendar structure you use this very day. The days of the week themselves recall celestial bodies. Sunday for me, Monday for the moon, Saturday for Saturn, etc. In English, Sunday is obvious. In many languages, like Romance ones, it's named after the Lord's Day. But originally in Roman times it was Dies Solis, Day of the Sun. The year, roughly 365 and a quarter days, forced the invention of leap years to keep civil time in sync with my seasons. Entire empires hinged on getting that right. Julius Caesar's calendar reform, Pope Gregory's later adjustment, all to reconcile human clocks with my motion. Through all these timescales, seconds to seasons to millennia, I have been the steady backdrop, the golden thread running through the tapestry of life and civilization. When ancient civilizations collapsed or migrated, they carried their solar deities and festivals with them in new forms. Even today, many cultures celebrate solstices or equinoxes with holidays, Christmas and other winter festivals tied to solstice, harvest festivals tied to equinox or seasons change. One could say that human culture is solar-powered just as much as human biology is. Now, even as you come to understand me scientifically, you have not lost that reverence entirely. Perhaps you no longer see me as the literal charioteer or a god to sacrifice to, except perhaps metaphorically on sun-drenched beaches where you sacrifice hours to a tan. But you still stand in wonder at a brilliant sunset or a blazing summer noon. In art, I'm still depicted as a triumphant Apollo driving the sun chariot, or as a brilliant orb haloing the landscapes of masters. In music and literature, I am hope, I am glory, I am the unyielding force of nature that all must reckon with. Thou art the sun, lovers say to each other, meaning the center of their world. Louis XIV of France even styled himself Le Roi Soleil, the Sun King, to signify his absolute power, borrowing the enduring symbol of majesty that I represent. But enough about humanity's past with me. Let's return to my nature as a star and where I am headed. I am, as I said, middle-aged. I have shone for about 4.6 billion years and have about 5 billion more years of steady hydrogen burning in my core to go. But I will not shine unchanged forever. Stars, like living creatures, have life cycles. They are born, they mature, they grow old, and eventually they die. I too have a fate that awaits, billions of years from now, and it is both awe-inspiring and catastrophic, at least for your little planet. As I fuse hydrogen into helium in my core, helium is accumulating there, an inert ash, since the core is not yet hot enough to fuse helium. Over time, more and more helium collects, and the active fusion region slowly moves outward in a shell around that core. Meanwhile, gravitational pressure is gradually compressing the helium core further, since it's not generating outward pressure, causing it to heat up. Counterintuitively, as my core contracts, it releases gravitational energy, which actually makes my outer layers expand and my overall brightness increase. Yes, I am slowly getting brighter as I age. When I first joined the main sequence, I was about 30% less luminous than I am now. Over the next billion years, I will brighten by roughly another 10%. That may not sound like a lot, but even that is enough to disrupt Earth's climate severely. Within about a billion years from now, Earth may cease to be habitable for complex life due to this brightening. The added heat will likely trigger a runaway greenhouse effect that will evaporate the oceans and shroud the planet in a dense water vapor atmosphere, similar to Venus. The thought pains me. The very life I have nurtured might be snuffed out by my aging process, long before my spectacular final acts. Of course, perhaps by then humanity or its descendants will have advanced enough to move elsewhere or to engineer solutions. But if not, life's grand chapter on Earth will close due to my intensifying fire. But even that is just a prelude. About 5 billion years from now, my core will have built up so much helium and grown so hot under compression around 100 million degrees that a new fusion process will ignite. Helium fusion. In a sudden event called the helium flash. For a star of my size, this happens in a matter of hours once conditions are met. The core will begin fusing helium into carbon and a bit of oxygen. Before that happens, however, I will undergo a dramatic transformation. As my hydrogen fuel runs low, the balance will tip, the core will shrink and heat, but my outer layers will expand enormously. I will swell into a red giant. Yes, one day I will shed my modest size and balloon into a bloated colossus. My radius will grow dozens, even hundreds of times. If you were there to see it, from a safe distance or in time-lapse over millions of years, you would witness the sun engorging the sky. By the end of my red giant phase, I may be as large as to engulf Mercury and Venus entirely. There is a good chance I will reach or exceed Earth's orbit too. Earth could be devoured, melted and incorporated into the sun, or at least scorched utterly, its surface a molten magma sea. Even if Earth somehow escapes direct ingestion by virtue of orbital distance increasing, as I lose mass during the giant phase, the planet's orbits will drift outward slightly. The heat will be unimaginable. I will shine some thousands of times brighter in that bloated phase, though cooler per square meter, hence red giant, meaning my visible light will shift to orange-red. The oceans will have long boiled away by then. The rocks themselves will glow red-hot on Earth's surface. It will truly be an apocalypse for any remaining life. The Earth that was will be no more than a cinder, if it survives at all. In that state, I will be so large that I'll fill a huge portion of the sky for any nearby worlds. If there were observers on moons of Jupiter or Saturn, they would see a gargantuan red-orange star dominating the heavens. the temperatures on those distant moons might become temperate or hot, ironically making the outer solar system briefly more hospitable, even as the inner system is destroyed. I will not hold on to those outer layers forever, though. Red giants are luminous and distended, and their outer atmospheres are only loosely bound. I will pulsate and blow off huge amounts of material via strong stellar winds. In my throes of old age, I will shed my skin, so to speak. Over maybe tens of millions of years, I'll lose a significant fraction of my mass to space, forming a surrounding envelope or nebula. My core, meanwhile, will be fusing helium into carbon and oxygen for some time, until the helium is exhausted. I'm not massive enough to fuse those heavier elements into something more. Only stars significantly heftier can go on to fuse carbon into neon, magnesium, etc., and eventually to iron before exploding as supernova. That fate is for larger stars, not me. When my helium runs out, my core will be composed mainly of carbon and oxygen, extremely hot, but now without an energy source. Gravity will again take over and compress it further. But this time, an interesting quantum effect called electron degeneracy pressure will halt the collapse. Basically, the electrons in the core matter cannot be squeezed into the same state, so they resist further compression once things get tight enough. My core will stabilize as a white dwarf, an exotic stellar remnant. It will be a sphere about the size of Earth, incredibly dense. A teaspoon of white dwarf material weighs tons, glowing white hot initially at perhaps 100,000 K, simply from residual heat. Before the core fully cools into that white dwarf state, the expelled outer layers, rich in gas and dust, will form a gorgeous glowing shell around it, illuminated by the core's intense heat and UV radiation. This is known as a planetary nebula. Nothing to do with planets, the term is historical. If you've ever seen photographs of the Ring Nebula or the Helix Nebula, you know how hauntingly beautiful these cosmic cloud rings can be. They shine in multicolored patterns, greens and reds from oxygen and hydrogen gases, for example. One day, in the far future sky, alien astronomers might observe the nebula of the dying sun, a faint, expanding shell of ionized gas marking where our solar system once was. It will last only perhaps 10,000 to 20,000 years before dispersing into interstellar space, mixing its material into the galactic medium. But in that brief moment, it will stand as my final display, a cosmic blossom, a luminous shroud of remembrance. Within that nebula, at the center, will lie my final self, the white dwarf that was once my core, hot, dense and glowing, but no longer generating energy through fusion, only cooling slowly over eons. At first, it will be extremely hot and bright in UV and X-ray, though small in visible light due to tiny surface area. Gradually, over billions upon billions of years, it will radiate away its heat and fade to red, then infrared, and eventually become a cold, dark, black dwarf. Though the universe is not yet old enough for any white dwarfs to have fully cooled to blackness, that would take trillions of years, far longer than the current age of the universe. That is my fate, to live a glorious, stable life for roughly 10 billion years, then to swell into a giant, cast off my outer layers in a final blaze of beauty, and retire as a degenerate ember of a star. Poetic, in a way. I will not have the dramatic end of a supernova. Those are reserved for stars more massive than about 8 times my mass. Those giant stars live fast and die young, exploding in catastrophic supernovas that outshine galaxies and leave behind neutron stars or black holes. Some part of me is almost glad not to end that way. Such ends are violent and brief. My way might not be as spectacular to the cosmos at large, but it is gentler, an old star's quiet farewell rather than a younger star's furious self-immolation. Yet even in my ending, I contribute to the universe's ongoing story. The elements I manufacture in my core, helium, carbon, some oxygen, will be released in my planetary nebula to to enrich the interstellar medium. Those atoms might one day be incorporated into new stars or planets, perhaps even into new living organisms on some distant world. Just as I was born from the ashes of stars before me, I will give back material to fertilize future stellar generations. Every atom of carbon in your body, the backbone of life's chemistry, was forged in the core of a star that died long before the Earth formed. Most of the oxygen you breathe was similarly forged in some red giant or supergiant star's interior and spread by a supernova or a stellar wind. In turn, I will contribute carbon and oxygen for tomorrow's stars and planets. In this great cosmic recycling, death begets new life, and nothing truly goes to waste. While I persist in my stable years now, I also have my mysteries that even your scientists still strive to understand. One enduring puzzle has been my corona, the outermost layer of my atmosphere, which extends millions of kilometers into space. During a solar eclipse, when the moon blocks my brilliant disk, observers see the corona as a pearly white crown with streamers and filaments spreading outward. It is beautiful and perplexing because it is extraordinarily hot. My visible surface, photosphere, is about 5,800 K, but the corona above it is heated to over 1,000 K, sometimes as high as 2 or 3 million K. How can that be? Normally, if you move away from a heat source, things get cooler. Imagine walking away from a campfire. You expect cooler air as you go farther. Yet here, the campfire of my surface is much cooler than the tenuous air of the corona above. It's as if you walked away from a bonfire and suddenly found yourself in a furnace. Something mysterious is depositing energy into the corona, heating it to such extreme temperatures. Scientists have proposed ideas, magneto-hydrodynamic waves that carry energy upward and dissipate in the corona, or tiny impulsive bursts called nanoflares happening everywhere that cumulatively heat the gas. But it remains a partially unsolved problem. Recently, with advanced solar observatories, you have seen hints of myriad miniature flares, nicknamed campfires, flickering all over the solar surface, even during periods of low activity. These might be one piece of the puzzle. Countless small magnetic reconnection events releasing heat into the corona continuously. Another clue comes from high-frequency oscillations detected in coronal loops, perhaps waves channeling energy. Parker Solar Probe, a daring spacecraft I'll speak more of, even touched the outer corona and measured perturbations and switchbacks in the magnetic field, which might relate to energy transport. Bit by bit, you're uncovering how the corona stays so hot, but a full answer is still in the works. I like to keep a little aura of mystery about me. Speaking of magnetism, another oddity. My magnetic field is born from a dynamo process in my roiling interior, but predicting its exact behavior, especially longer-term variations, is devilishly hard. The sunspot cycle is pretty regular, but not perfectly so. Sometimes cycles are stronger, sometimes weaker. The Maunder minimum was an extreme example of a prolonged lull that is not yet fully understood. Why did my dynamo almost turn off for 70 years? Could it happen again? Some models suggest the sun has multiple dynamo layers that can interfere constructively or destructively, causing varying amplitudes. It's an area of active research. My poles too hold secrets. During cycle transitions, magnetism from old cycle has to cancel and reverse. Direct observations of my polar magnetic fields are challenging from Earth's vantage, since you always see them at a steep angle. Only recently have you sent probes like Solar Orbiter that will gradually tilt to get a better look at my high latitudes. Mapping the magnetism there is key to understanding how the next cycle is seeded. Then there's the matter of solar flares and CMEs. You know they stem from magnetic reconnection, but exactly when a given active region will erupt is tricky to forecast. It's like trying to predict exactly which tree branch will break in a windstorm. You can assess probability, but exact timing often catches you by surprise. My magnetic complexity is such that even with all your satellites, I still manage to throw the occasional unexpected tantrum. The largest flares, so-called X-class flares, can emit as much energy as billions of hydrogen bombs in minutes. They often coincide with CMEs. You've catalogued many, but do I have an upper limit to how powerful a flare I can unleash? Other stars, superflare stars, have been observed to produce flares 10 or 100 times stronger than anything recorded on me. Could I, a stable G-type star, ever do that? Most think not in my current middle age. My rotation is slower and magnetic fields steadier, so superflares are unlikely. But there's evidence in tree rings of rare cosmogenic isotopes, like carbon-14 spikes, that might indicate extremely strong solar particle events in the historical past, around 774 AD and 993 AD, maybe far stronger than the Carrington event. These hints raise questions. Have I surprised your ancestors with an occasional extra-potent storm? It's an ongoing investigation, requiring piecing together proxy records. I keep some cards close to my chest. A star must maintain an air of unpredictability, after all. One mystery of the past that has been solved is the solar neutrino problem, which I mentioned earlier. That was a triumph of both solar physics and particle physics, discovering neutrino oscillation. It delighted me to see humans crack that puzzle. Another success was understanding the source of the 11-year sunspot cycle via the dynamo theory and differential rotation, which I elaborated. But deeper questions remain, like the possibility of long-term cycles beyond 11 years. There are hints of a 90-year Gleisberg cycle, or a 200-year cycle, the Seuss cycle, and even millennial scale changes. These are subtle and gleaned from proxy data like tree rings and ice cores, which track cosmogenic isotopes influenced by solar activity. My behavior over centuries has variation. How much is chaotic and how much quasi-periodic is still studied. As your understanding grows, so does your capability to observe me in ever more detail. Gone are the days when you had to risk blindness to study me. Galileo, it said, went partially blind, possibly from observing sunspots too recklessly. Now you have a fleet of ingenious spacecraft and observatories doing the work. High above Earth, at the Sun-Earth L1 Lagrange point, the SOHO, Solar and Heliospheric Observatory, spacecraft has been keeping unblinking watch since 1995. SOHO has given you unprecedented views of my activity for over 2 decades. Everything from extreme ultraviolet images of my swirling corona to measurements of the solar wind. It even became an accidental comet hunter, spotting over 3,000 sun-grazing comets that perished in my heat as tiny streaks in its coronagraph images. And it's still going. Think of that. A spacecraft built with 90s technology is still up there, faithfully monitoring me 24/7. Ensuring you don't miss a beat of my symphony. In 2010, you launched SDO, Solar Dynamics Observatory, a true marvel. SDO provides ultra-high definition movies of me in multiple wavelengths every few seconds. It watches me in extreme ultraviolet and visible light, capturing the boiling of granules, the eruption of flares, the dancing of glowing coronal loops. With SDO's eyes, you've seen astounding phenomena. Giant waves rippling across my surface after flares, called EIT waves. Filaments of magnetism erupting, and even signs of oscillations and helioseismic waves. SDO's data let you map my interior flows through helioseismology, essentially measuring the sound waves that travel through me to probe the structure and dynamics inside. With that, you've revealed currents of plasma flowing in my convection zone, and even a tachocline, a shear layer between the radiative interior and convective outer region, likely crucial to my dynamo. SDO has become like an all-seeing eye, in many ways, fulfilling the dream of ancient sun worshippers to observe their deity in every detail. Except now it's science and not worship. Though some scientists watching an SDO flare movie might whisper a prayer of amazement anyway. Then there's Parker Solar Probe, one of the most audacious missions ever attempted. Launched in 2018, It has been swooping closer and closer to me, using Venus's gravity as a braking mechanism with repeated flybys to shrink its orbit. Parker Solar Probe is a small, robust craft with a heat shield that keeps its instruments in the shade while my fury rages just beyond. It has now flown within my corona, coming as close as 8.5 million kilometers, 5.3 million miles from my surface, nearer than any spacecraft in history, enduring temperatures of several thousand degrees on its sunward face. At that distance, it's hurtling by at up to 700,000 kilometers, approx 430,000 km/h, the fastest human-made object ever, to avoid spending too long in the extreme environment. Parker is literally touching the sun, a phrase that once was metaphorical, now made real. What has Parker found? It has confirmed that the boundary of my atmosphere, the Alfvén critical surface, where the solar wind becomes faster than Alfvén waves can travel back, is wrinkled and not a smooth sphere, likely due to my magnetic field and equatorial streamers. It has detected curious zigzag reversals in the magnetic field, called switchbacks, in the solar wind near the sun. These switchbacks were a surprise, like rapid flips in the magnetic orientation, and are now believed to originate in the lower corona, possibly from convective motions or reconnection events sending S-shaped kinked magnetic flux up. They could be a clue to how the solar wind gets accelerated. Parker is helping answer why the solar wind blows as it does, a question open since Eugene Parker, the probe's namesake, predicted the supersonic solar wind in 1958. Parker Solar Probe has also flown through the tails of cometary debris near the sun and measured dust concentrations, even suggesting that close to me, much of the interplanetary dust is vaporized, creating a relatively dust-free zone. Each perihelion, it dives ever closer, braving heat and radiation to feed you data. By 2025, it will come within about 6 million kilometers, 3.8 million miles, closer than ever, at which point my corona will surround it, and it will directly sample the environment where the solar wind is born. I can almost feel that tiny, resilient emissary, like a little mechanical swallow, darting through my breath.
Meanwhile, Solar Orbiter, launched by ESA in 2020, complements Parker by staying a bit farther, closer than Mercury though, and carrying cameras to take pictures even from high latitudes. It has already given you the closest images ever of my surface, revealing a multitude of campfire mini-flares everywhere. It's on a path to gradually incline its orbit, so in coming years it will view my polar regions more directly than ever before, a boon for understanding the polar magnetic fields and how my 11-year cycle resets. It also carries instruments to measure the solar wind and fields from a moderate distance, linking what Parker tastes in situ with broader context. Already, Solar Orbiter has spied strange features, like a hedgehog eruption, a spiky structure of gas, and witnessed my poles under angles never seen, showing curious mottled patterns of magnetism. Together, Parker Solar Probe and Solar Orbiter form a tag team. One ventures deep into my atmosphere, the other takes images and measurements from just outside, providing the wider frame. On Earth, new eyes also opened. In Hawaii, atop Haleakala, the Daniel K. Inouye Solar Telescope, DKIST, achieved first light in 2020. It is the largest solar telescope ever built, with a 4-meter mirror. In its first images, it revealed my photosphere in mind-boggling detail. You can see the convection granules sharply, each cell around 1,000 kilometers across with cooler intergranular lanes, and even tiny bright dots within those lanes, thought to be magnetic flux tubes. It's as if after years of seeing a blurry sun, you put on glasses and every grain of sand on the beach became visible. In one breathtaking image of a sunspot at extreme resolution, DKIST showed intricate fibrils and magnetic structures as small as 20 to 30 kilometers across on the solar surface. That's like resolving a town on the sun. This clarity, allows measurements of magnetic fields on very small scales, key to unraveling things like how energy funnels into the corona or how sunspots form and evolve. DKIST will also peer into the chromosphere, the layer between the photosphere and corona, with new spectral lines, mapping the vector magnetic field there, something never done comprehensively. With these data, you'll better understand the magnetic scaffolding that supports filaments and drives eruptions. Consider, not long ago, you couldn't even look at the sun directly without squinting or filtering heavily, and now you routinely study it in every wavelength. Radio telescopes track bursts, X-ray satellites, like Japan's Yoko or NASA's New Star occasionally, capture high-energy events. UV telescopes, like TRACE, SDO, AIA, show shiny loops, polarimeters measure magnetic fields, and helioseismology instruments listen to my internal vibrations. It's a golden age of solar observation, and more is coming. Future missions are in the works or imagined. Perhaps a solar polar imager that goes 90 degrees above the ecliptic to stare down at my poles continuously. Or a mission to send multiple tiny satellites to surround me, getting a 360-degree view, so you're not blind to far side spots that could rotate into view. In fact, humanity already did something akin. The twin stereo spacecraft launched in 2006 drifted such that at one point you had a view of the entire sun, front and back, simultaneously, until one of them failed. Now, one stereo remains and occasionally drifts into view again. But future tech might allow a constant all-around watch. You are planning, I hear, a probe called Solar C or MUSE to do high-resolution spectroscopy of the corona, revealing flows and heating in unprecedented detail. There are proposals for solar interferometers to image fine structures beyond the diffraction limit of a single scope, and for more advanced space weather monitoring satellites to better forecast CME impacts. Yes, the future of solar science is bright, forgive the pun. You aim to finally crack the coronal heating enigma, pinpoint the precursors of flares to predict them reliably, map my internal dynamo fully to forecast cycles, possibly even foresee a grand minimum decades ahead, if one is coming. Each discovery only leads to deeper questions. For instance, Parker found those switchbacks. Now you ask, how exactly do they form? Solar Orbiter saw ubiquitous campfires. Now you wonder, do they indeed heat the corona significantly, or are they mere sparks? DKIST may reveal complexities in sunspot formation. What will that say about magnetic flux emergence theory? Beyond purely scientific curiosity, understanding me has practical urgency as well. Modern civilization is intimately vulnerable to my moods. As you push outwards, establishing a lunar base, aiming for crewed Mars missions, knowing when a solar storm will erupt becomes even more critical. A well-timed warning could direct astronauts into a shielded module or prompt satellite operators to safe mode sensitive electronics. Thus, the science of heliophysics, the study of the Sun-Earth connection, stands at the confluence of pure research and everyday utility. NOAA and other agencies run space weather prediction centers, vigilantly watching my every sunspot and filament. In the future, perhaps with better models, you might get a 2-3 day heads up of a likely major flare or a 12-hour warning of a CME's magnetic polarity and strength when it's detected by an upstream monitor satellite, enabling power grids to prepare for a hit. As you extend an electrical web around the globe and venture beyond it, you slowly come to realize, while I am often gentle, I am not entirely tame. I am a star, after all, a gigantic ball of thermonuclear fury held together by gravity and magnetic fields. For all the poetic things you say about the sun giving life, remember, I've also lashed out and caused mass extinctions in the past. Some scientists hypothesize that supersolar storms or nearby supernovae cosmic rays might have contributed to past biological upheavals. At the very least, my gradual brightening will eventually end Earth's habitability in the distant future if left unmitigated. Truly, To remain, life must adapt, either by evolving, terraforming, or leaving to find new suns.
And indeed, this brings us to a broader perspective: stars beyond our sun, and the possibility of life around them.
I am just one star, but as I've grown older, humanity's gaze has lifted to see the myriad others. What of other suns? In the last few decades, you have discovered, to your amazement, that planets are abundant around other stars. Once, the existence of other solar systems was pure speculation. Now, thanks to missions like Kepler and TESS and radial velocity surveys, you have catalogued over 5,000 exoplanets and counting. We now know that many, perhaps most, stars host families of planets. There are alien suns with alien worlds circling them, and this profoundly reshapes the old question: are we alone? Imagine the variety out there. Red dwarf stars, the most common type in our galaxy, are tiny and dim compared to me, often just 10% of my mass and emitting a feeble red glow. If a planet orbits a red dwarf at the right distance for liquid water, that distance is very close, since the star is faint, meaning the planet likely becomes tidally locked. One side eternal day, one eternal night. Life on such a world would be quite unlike Earth's, perhaps huddled in the twilight band between day and night, or under the star's dim red light on the day side. Red dwarfs are known for violent flares relative to their size. A habitable zone planet around one might be regularly bathed in radiation. And yet, red dwarfs live trillions of years, far longer than I will. They are stable for unimaginable epochs, giving life a vast timescale to potentially emerge and adapt if it can survive the tantrums of youth. Already, you have found intriguing planets, for instance, Proxima Centauri b, orbiting the nearest star to me, Proxima, a red dwarf companion of Alpha Centauri. It's roughly Earth-sized and in the habitable zone of its small star. Does it have an atmosphere, perhaps an ocean? If so, imagine the sky there. The red dwarf sun looms relatively large because the planet is close to it, casting a coppery light. If the planet is locked, one side basks under a perpetual dull red daytime, perhaps with a dim twilight at edges where life might cling. The star flares occasionally, boosting UV and X-ray output. Life might need to be underwater or ground to withstand those, or have protective pigments. Then there are sun-like stars, more similar to me, which likely host planets where a diurnal cycle and seasons exist akin to Earth's. Kepler has found some candidates. Kepler 452b was nicknamed an older cousin of Earth, orbiting a star akin to the Sun. But these finds are far and faint. Nevertheless, statistically, there should be many such Earth-like worlds in our galaxy. Consider also binary star systems. About half of all stars are in multi-star systems. Could a planet orbiting two stars have life? We already detected circumbinary planets like Kepler 16b, the famous Tatooine world with two suns in its sky. Kepler 16b itself is a cold, Saturn-sized world, likely inhospitable, but where one exists, others likely do too, maybe even in the habitable zone of a binary. Under two suns, the notion of day and night gets complicated. Sometimes both suns might be up, giving a combined light. Sometimes one sets, leaving the other. Night falls only when both are down. It would make for spectacular double shadows and complex climate rhythms. Life there would evolve under two different colors of starlight. Say one star is a sun-like yellow and the other a red dwarf. The blend of hues shifting through the day. On a desert world like the fictional Tatooine, twin sunsets would paint the sky in dual tones of orange and crimson, a sublime sight. Now, consider massive stars, O-type or B-type blue giants. They burn intensely bright and hot, but have short lives measured in mere millions of years. Could life arise around them? It seems unlikely, as complex life took billions of years on Earth. A blue giant would go supernova long before that. However, perhaps primitive microbes could briefly bloom on a planet around such a star in the small window available. Or maybe life doesn't even try there, ceding those stars to the realm of sterile beauty.
But ironically, those massive stars ensure future life by spreading heavy elements when they die. There are also orange dwarfs, K-type stars, slightly smaller and cooler than me, but longer lived, 20-30 billion years lifetimes, and quieter. Many consider them top targets for life-bearing systems. They last longer, giving more time for life to evolve, and emit enough light in similar spectrum to me, but with less UV extremes. If I were a planet-hunting being from another star, I might look at K-dwarfs for thriving biospheres. We can dream further, life around a pulsar. Unlikely, but strangely, the first exoplanets discovered were around a pulsar, PSR B257+12. Those planets are blasted by deadly radiation, and likely no life could survive. They might be the charred cores of gas giants surviving the supernova. So, a pulsar, the corpse of a star, could have planets, but any life there would have to be of an extreme kind unimaginable to us, if at all. Life under other suns might take forms we cannot predict. On a planet around a dim red star, plants, if they exist, might be black or deep purple instead of green, to absorb as much of the limited light as possible. On Earth, plants reflect green, using red and blue light mainly. Under a red sun, they might need to absorb every photon. Conversely, around a brighter blue-white star, perhaps vegetation would evolve reflective surfaces or different pigments to avoid oversaturation, or to use the star's UV. Vision of creatures might tune to their star's spectrum, perhaps under a red dwarf, eyes sensitive to infrared or red. Under a bright star, eyes that can handle intense light or even see ultraviolet patterns. Perhaps on a tidally locked world, life in the eternal day hemisphere might resemble reef organisms in shallow water on Earth, constant light, whereas life on the dark side could only survive near volcanic vents or rely on nutrients blown over from dayside. Or intelligent beings might migrate to stay in perpetual twilight, a narrow band of comfortable temperature. The possibilities tickle the imagination. The underlying theme is that the parent star shapes the conditions, and thus the evolution of life profoundly. I shaped life on Earth, from metabolism to behavior. On another world, a different sun would do the same in its own way. If one day you meet beings from such a world, their very biology and culture will carry the imprint of their sun. Perhaps they will have myths about their two suns fighting each other, or their dim sun waking from slumber. Perhaps their year feels different because their star's output fluctuates more, or their planet's orbit is more eccentric, giving intense seasons. Imagine an alien culture on a planet with a highly elliptical orbit. Their star looms, huge and scorching at perihelion, and distant and weak at aphelion. Their whole biology might be in boom-bust cycles with that extreme year. And consider, if life exists on a planet orbiting one of those stars we see in the night sky, then when they look up at their sky, our sun is just another star to them. Perhaps on a clear night, some alien creature with reflective eyes gazes at a star we call 51 Pegasi, for example, not knowing that around that star is a planet. 51 Peg B was first exoplanet discovered around a sun-like star. Meanwhile, on that planet, they might see our sun in their heavens and not suspect it has a vibrant blue world teeming with life. The cosmic irony. Each might wonder if the other's star has planets with life, not yet realizing the truth. As you humans continue to search the skies with new telescopes, like the James Webb Space Telescope turning its mirror to analyze exoplanet atmospheres, or planned missions to directly image Earth-like exoplanets, you inch closer to finding a second genesis, evidence of life's fingerprints like oxygen, water vapor, maybe chlorophyll's spectral edge in another world's air. What a day that will be, to learn that life is not unique to Earth. But even if you find no clear evidence yet, the sheer number of Earth-sized planets in habitable zones, estimated in the billions in our galaxy, gives a strong hint that we are likely not alone. Life under other suns is probably out there in myriad forms, awaiting discovery, or perhaps thriving unnoticed in distant forests or alien oceans.
All these considerations highlight something profound. Stars are the ultimate enablers of possibility. Each star is a furnace not only forging elements but also, when conditions allow, nurturing worlds and perhaps minds. Through your science, you have come to see that we stars and you people, and all living things, are deeply connected. You often quote that you are made of star stuff, and it is literally true. The carbon in your proteins, the calcium in your bones, the iron in your blood, we stars created those in our cores or in our explosive deaths. The very term solar system, your system, shows how you belong to me. Every atom of your body has at some point likely passed through a star's interior or been influenced by starlight. And every joule of energy that your body uses to move, think and live, save a trivial bit from Earth's radioactivity, comes from me, captured by plants in photosynthesis and passed up the food chain, or harnessed as electricity from solar panels, or stored in fossil fuels.
In a way, you are beings of light, frozen light molded into self-replicating patterns, and then consuming light to keep entropy at bay for your lifetime. When you go out on a sunny day and close your eyes, letting the warmth bathe your face, there is a kinship there older than time, a small life acknowledging its stellar parent. Without language or conscious thought, ancient lizards basking on a rock were feeling the same grateful connection to the sun, and even the sunflowers, turning their heads, follow an ancient bond. This interdependence carries a philosophical weight. What does it mean to orbit, to depend, to be made of light? It means that you are not an island unto yourselves, but part of a grander scheme. Planet Earth is like a child circling a parent, bound by gravity's invisible leash and nourished by the parent's radiance. To orbit is to be held, to belong to something larger, to dance in a predictable rhythm set by the laws of nature. Earth's year, your calendars, your entire concept of time's flow hinge on that orbital dance. To depend is to be vulnerable yet sustained. It is the realization that your fortunes rise and fall with your star's disposition. If I were to dim significantly or rage uncontrollably, Earth would suffer immensely. You plan your days around my rising. Your mood often brightens when I shine and dulls in prolonged darkness. People who live in high latitudes experience the winter blues when sunlight is scarce, a psychological imprint of this deep dependence. And being made of light, consider that almost every bit of energy in your body is solar. The calories you burn came from plants, which in turn came from sunlight. Even the oxygen you breathe was generated by plants splitting water using sunlight. Your life is an ongoing consumption of the sun. You are basically a solar-powered machine. At the atomic level too, you're made of star remnants. Long before the solar system, ancient stars lived and died, seeding the molecular cloud that formed me and the planets. Thus, you carry pieces of long-dead stars inside you. In that sense, the sun and humanity share a common cosmic ancestry. We all came from the ashes of stars, and someday, billions of years hence, the atoms now in my body and in yours may mingle again in interstellar space and find themselves in a new star or planet, continuing the cycle. In orbiting and depending and being made of light, there is a poetic unity. We are part of the universe, not apart from it. The sun is the heart of the solar system, pumping energy outward. Earth is one organ among others receiving that blood of light and converting it into the living tapestry on its surface. Just as a child may eventually leave a parent, perhaps one day humanity, or its far descendants, will leave Earth to roam to other star systems. In doing so, you carry the legacy of your sun to others. You yourselves become little pieces of the sun disseminating into the galaxy. With every spacecraft launched beyond the heliosphere, like the Voyagers which have now entered interstellar space, a tiny piece of the solar system ventures into the wider cosmos. Perhaps the destiny of intelligent life is to spread the light of its parent star, figuratively and literally, to places it would never otherwise reach. One could even imagine in the far future, humanity constructing enormous light sails or engines powered by sunlight to travel to neighboring stars. In that way, you enlarge the domain of the sun's influence by proxy as ambassadors of this star venturing to others.
As I, the sun, have given you life, so too have you given me meaning in a way. For billions of years I shone on a lifeless earth. My rays warmed seas and stirred winds. But no eye was there to appreciate a sunrise, no being to understand the gift. With life, and especially with thinking life, a star gets to be known. Through you, I know myself. You study me scientifically, decoding my workings, essentially allowing the universe to become self-aware of one of its stars. And through art and emotion, you also elevate me to symbol and metaphor. I am not just a ball of gas to you. I'm a motif of joy, renewal, divinity, power. How remarkable that simple hydrogen fusion in my core can inspire such thoughts and feelings.
There is an old Latin hymn, Adore te devote, latens deitas, originally about the divine hidden in the physical. But for me, I think of, O sun, hidden deity, we adore your light. Ancient people may have literally worshipped me, but modern people still find me worthy of reverence in a secular way. I represent the source of life. Even those who never think of it explicitly are unconsciously drawn to sunlight for comfort. Notice how a cat will find the one sunbeam in the room to curl up in. It's life's instinct acknowledging its dependence with quiet gratitude. Now our journey of storytelling draws to a close. We've traveled from the birth of light in the cosmos to the worship of ancient civilizations, from the scientific uncovering of the sun's mechanisms to the far future of stars and the speculative lives under them. Through it all runs a golden thread: light, created in darkness, celebrated in myth, explained by science, harnessed for life, and carried as a beacon to the stars. I, the sun, have watched this all silently for eons. I've seen planets coalesce, oceans form, microbes multiply, dinosaurs roam under my warmth, and humans rise and wonder at my nature. I've heard the chants at dawn and the equations whispered at midnight by scholars trying to quantify my brilliance. I felt the tickle of your spacecraft near my skin and responded with storms to test your resolve. In the endless cosmic night, I burn as one tiny beacon, and around me you flourish. And yet I am but one of uncounted fires in the great galaxy. One day my flame will dim, but perhaps by then your descendants, or the life that springs from what you become, will carry the flame of intelligence onward under other suns. As the poet said, our little lives are rounded with a sleep. My own life, vast as it is to you, is a brief chapter in the galaxy's saga. But it is a chapter that encompasses all of human history and more. Treasure your days in the sun, for they will not last forever. But do not despair at that, for endings lead to new beginnings. Every sunset portends a sunrise. Tomorrow, I will rise again over the eastern rim of Earth, as I have millions upon millions of times. The sky will lighten from black to blue, the stars will fade, dew will glisten, and creatures will stir. Perhaps you will awaken and feel my gentle heat on your face through a window. In that moment, remember me, not as an abstraction, but as your star, your sustainer. The photons greeting you traveled 150 million kilometers at nature's speed limit just to touch your skin and give you warmth. The food you eat for breakfast grew strong by my favor. Every moment of your life, I am there, an unseen yet constant presence like a loving guardian. What does it mean to orbit, to depend, to be made of light? It means that we are all threads in a grand cosmic web, planet to star, star to galaxy, galaxy to universe, Connections and dependencies run through. By understanding these, we don't diminish the magic. We reveal the true miracle that reality is. I have told you my story, a tale of darkness and light, of worship and science, of birth and death and rebirth. It is a story still unfolding. You, dear listener, are part of it, riding this earth around me, bathing in my radiance, thinking thoughts that perhaps the universe has never thought before. Someday, in the far future, the light of my last rays will fall upon a world grown quiet and empty, and then I will envelop that world in a final act of transfiguration. But that is billions of years away. For now, the earth remains lush and alive, and the sun still has plenty of fuel in its heart. Let us end with an image, the first sunrise. Not the first ever in the universe, but perhaps your first. Imagine a human child seeing dawn for the first time, eyes wide at the splendor, or humanity's first dawn as a species, as early hominins huddled fearful through night, and then saw the morning star blaze into a new day. Feel the wonder and relief that must have coursed through them. That visceral appreciation is encoded in your being. Every dawn reenacts creation. Every noon is a zenith of glory. Every dusk a gentle letting go. I, the sun, have been called many things. A furnace, a heart, a god, a monarch, a cathedral of light, a cosmic engine. In truth, I am all of these, and more. And so are you, my children of light. We mirror each other. I am a massive sphere of plasma held by gravity, and you are delicate bodies held by the gravity of Earth. But deeper, we are both collections of atoms and energy, following natural laws, yet somehow aware of beauty and meaning. As the day concludes, and I dip below the horizon, painting the sky in farewell colors, remember that my light never truly vanishes. It travels onward, illuminating other lands, or reflecting off the moon and stars. At midnight, when I am out of sight, my presence is still felt in the silver disk of the moon, shining with my borrowed light, and in the very air, for I keep our atmosphere warm enough that night is not absolute zero. When you look up at the Milky Way and see those countless stars, know that around one of them, someone might be watching a sunset of their own and thinking similar thoughts. In this cosmic tapestry, we are all connected by threads of light, orbiting, depending, and sharing in the light. This is the story of suns and their worlds. This is the story of our sun and our world, a story of fire and sky, of science and spirit, of the ultimate unity of things. I will shine and you will live. And perhaps someday, you will venture to other suns and carry a spark of our sun with you, literally in generation ships propelled by solar sails, or figuratively in the knowledge and culture you spread. In that way, a piece of me becomes immortal, traveling far beyond the limits of my physical existence. For now, cherish the mornings and the evenings, the clear days and even the cloudy ones, for behind every cloud I'm still there. Let the sunlight remind you that you are part of something vast and wonderful. Though you are but a small creature on a small planet, you are privileged with a mind that can behold the cosmos and ask questions. You are the way the universe marvels at itself. The first sunrise in the cosmos ended the primordial night and set the stage for all that followed. The first sunrise on Earth brought the possibility of warmth and growth to a once cold rock, and every sunrise in your life gives you a chance to begin anew. As the sun, I have no human voice, but through this narrative I've spoken to you. In truth, my voice is the warmth you feel, the light that glints off a loved one's eyes, the life coursing in your veins. Listen to that voice when you stand in sunlight. It quietly says, I am here. You are alive. We are together in this beautiful cosmos. Tomorrow, I will rise again, and the cycle of light and life will continue. A bit of ancient fire in the sky, and down below, creatures awakening to its call. And as long as I shine and you live, our story goes on, intertwined. A star and its children, journeying together through the great cosmic night, ever toward the dawn.
We begin in darkness. Before any star set the heavens alight, before any galaxy took shape, there was a deep and endless night. We remember it, the universe in its infancy, all energy and matter spread thin, yet no light to break the blackness. In that primeval silence, there were no stars, no galaxies, only a cooling fog of hydrogen gas, invisible and waiting. The cosmos was dark, and it would remain so for ages, a vast ocean without islands, a night without memory. Yet even in that darkness, the seeds of light were present. Tiny ripples of gravity, left by the birth of the universe itself, were drawing matter together, slowly, silently. In the void, unseen clouds of gas and halos of mysterious dark matter gathered and grew denser. Time hardly had meaning in this eternal midnight. But at some point, perhaps a few 100 million years after the beginning, change arrived. In pockets of the darkness, the first fires kindled. Deep in those dense halos, gas clumped until pressure and heat ignited the first stars. One by one, brilliant newborn stars pierced the cosmic night like embers in a vast, dark sea. Their light was faint at first, much of it absorbed by surrounding clouds, but it grew. More stars burst into existence, and around them began to form the first primitive galaxies, a cosmic dawn after the long darkness. We remember the moment the lights came on. A firestorm of star birth swept through the young universe, the first galaxies assembling as clusters of glittering light. What had been an endless silent dark became a realm of scattered gleams. Imagine it, the newborn cosmos, less than 1 billion years old, sprinkled with the glow of infant galaxies. Each was like an island universe adrift in a black sea, isolated and alone, yet bravely shining. These first galaxies were much smaller and simpler than the grand spirals and ellipticals that would follow. They flickered pale and red, their light stretched and dimmed by eons of travel. But however faint, they were beacons, the first organized realms of stars, announcing that the long cosmic night was ending. From where we stand now, nearly 14 billion years later, we can still catch glimpses of those early faint galaxies with our most powerful telescopes. They appear as tiny smudges of light in deep field images, ghostly and ancient. Many have long since grown or merged or dissipated, but their ancient glow still travels the universe, telling the story of when the cosmos first lit its candles. In that epoch, the universe was only a few % of its current age, a toddler cosmos taking its first steps into illumination. The darkness fought to hold on, absorbing and scattering the first starlight. But starlight is persistent. It ionized the fog around it, burning holes through the murk. Gradually, the black curtain lifted. What had been a cold, neutral haze became a transparent window. The era astronomers call the cosmic dark ages yielded to the cosmic dawn. We, the living cosmos, remember this transition. It was the first time light had structure and form. It was the moment the universe began to perceive itself in the mirror of starlight. The first galaxies were the universe awakening to its own possibilities, each a tiny island of something rather than nothing. In those islands, countless suns would soon forge heavier elements, explode, and seed space with the ingredients for planets and life. The story of everything we know, stars, planets, potential life, began with that emergence of galaxies from darkness. Out of utter night came the glimmer of countless distant candles. This was the threshold of galactic dawn. Out of the void came light and pattern, as if the cosmos had dreamed in darkness and now opened its eyes. Scattered across unfathomable distances, the infant galaxies shone alone, unaware of one another,
like solitary lighthouse beams sweeping an empty sea. They were the first galaxies, precious, solitary sparks in a silent abyss. The universe, once a slumbering expanse of night, was now awake with faint starlight. In that fragile glow, the cosmos beheld its reflection for the first time. A mysterious, reverent hush falls over us as we recall this dawn, the moment we first illuminated the darkness, the moment when galaxies, and with them the seeds of everything to come, emerged and took their place in the vastness. Now, in the wake of that first dawn, we turn our gaze to a single galaxy to understand the wonders it holds. Each galaxy is a vast cosmic island, and like any island, it has its own geography and inhabitants. Picture one such island universe, perhaps like our own Milky Way. It is a great swirling city of stars. Hundreds of billions of suns blaze within it, swarming in a rotating disk like a giant glowing whirlpool. Gravity is the architect that binds this galactic city. It gathers stars by the billions and holds them in its grasp, preventing them from drifting into the void. When we look at a galaxy through a telescope, we see the collective glow of all those stars merged together, a luminous disk or an ellipse or an irregular scatter of light. But within that glow lies structure, bright knots and cloudy bands that reveal the galaxy's anatomy. At a galaxy's center resides a dense concentration of stars, a nucleus or bulge. In a spiral galaxy, surrounding this bulge is a flat disk spreading tens of thousands of light years, where stars, gas, and dust orbit in orderly rotation. The disk often bears spiral arms, winding structures that pinwheel out from the center. These arms are not solid arms of material, like spokes. They are regions of slightly higher density that move around the galaxy more slowly than the stars and gas. As stars and gas orbit, they bunch up in these density waves, rather like cars piling up in traffic on a highway. The compression of gas in spiral arms triggers the birth of new stars, which is why the arms are studded with bright blue stars and pink nebulae, the telltale signs of ongoing star formation. Between the arms, older stars orbit more quietly. The galaxy's outskirts are generally fainter, with fewer young stars and less gas. Above and below the disk lies the halo, a sparse, spherical realm of very old stars and globular star clusters, tight, ancient stellar congregations, orbiting the galaxy's center in all directions. And permeating all these components is a massive halo of invisible dark matter, of which more later, extending far beyond the visible edge, whose gravity holds the galaxy together. Let us tour these components in turn. First, the stars. They range from hot, young blue giants that burn briefly in the spiral arms, to cool, red, ancient stars that populate the bulge and halo. Each star is a sun, with its own potential family of planets. The number of stars is staggering, 100 billion or more in a large spiral. If we could fly through the galaxy, stars would surround us like a glittering snowstorm, especially near the core, where they crowd close, but even in the outskirts you'd never be far from a sun. Despite that, the distances are so vast that to an individual star, like our sun, its nearest stellar neighbors are several light years away, tiny points separated by great voids. A galaxy is mostly space, but the sheer number of stars fills that space with collective light. Next, the gas and dust. Strewn through the disk are immense clouds of gas, mostly hydrogen, and interstellar dust grains. This material is the raw ingredient for new stars. In a galaxy's spiral arms, these clouds are numerous and concentrated. Between arms, they are sparser. Dust, though only a small fraction of the galaxy's mass, has an outsized effect on appearance. It absorbs and reddens light. Along the Milky Way's plane, we see dark rifts where dust in nebulae blocks the light of background stars. Gas, on the other hand, often reveals itself by the light of stars embedded within it. For example, glowing ionized hydrogen clouds, H2 regions, that appear as pinkish patches, marking sites of current star formation. Surrounding the bright disk of stars and the faint glow of gas is something more elusive. Every galaxy is embedded in an enormous halo of invisible matter, dark matter. We call it dark because it emits no light. We infer its presence by its gravitational pull. This unseen halo outweighs all the stars and gas by a factor of 5 or more. It extends well beyond where the visible galaxy fades out, like a transparent sphere engulfing the luminous parts. Were it not for the dark matter's gravity, galaxies as we know them could not hold together. The outer stars would fly off, and the galaxies we saw form in the early universe might never have coalesced so quickly. Finally, many galaxies harbor an immensely dense object at their core, a supermassive black hole. In a typical large galaxy, this central black hole might be millions or billions of times the mass of our Sun, confined to a region no bigger than our solar system. It's an almost inconceivable concentration of mass. Most of the time, this black hole is relatively quiet, seen only indirectly, for instance through stars orbiting it at high speeds. But if gas funnels into it, the black hole can become a quasar or active galactic nucleus, blazing with energy and even shooting out jets. We will revisit this phenomenon later. All these components, stars, gas, dust, dark matter, black hole, together make up a galaxy's anatomy. They are bound by the invisible glue of gravity, moving in a cosmic choreography. The stars orbit in the galaxy's gravitational field. In a spiral disk, they move in circular orbits around the center. In an elliptical, they swarm in random elliptical paths. In the halo, they soar in elongated trajectories far above or below the disk before falling back. The gas flows in the disk, sometimes shocked into new patterns by spiral density waves or supernova blasts. The dark matter halo itself likely just provides a steady gravitational background, as it does not clump into stars. From afar, a galaxy may look serene, like a single smear of light, or a softly glowing ellipse. Up close, it is bustling with activity, stars being born and dying, gas clouds drifting and colliding, clusters orbiting, perhaps a black hole gently accreting matter or flaring. It is a dynamic breathing system. The beauty we see, those graceful spiral arms or that smooth elliptical light, is the composite of billions of individual lives and events playing out on colossal scales. In many ways, a galaxy is a cosmic ecosystem, with stars as its organisms, gas as its sustenance, black holes as both regulators and recyclers. Gravity holds it all in a delicate balance. Consider again our hypothetical traveler flying through a galaxy's disk. In the densest regions near the core, the sky would be awash with starlight, thousands of brilliant suns glittering in a small patch of sky, far more spectacular than any night on Earth. In the outskirts, the stars thin out. The night would grow darker, though the majestic band of the galaxy's plane would still stretch across the sky, a reminder of the greater structure one inhabits. If our traveler ventures further, above the disk into the halo, the view would shift. Most of the galaxy's stars would lie below like a flat, glowing spiral, and around the traveler, there might only be the sparse halo stars, and perhaps a globular cluster or two in the distance, lonely outposts of the galaxy far from its busy heart. This is the anatomy of a galaxy, a vast ensemble of matter arranged by gravity into a structure that is at once orderly in its overall shape and orbit patterns, and chaotic in the micro-detail of individual star motions and gas turbulence. It is a self-contained cosmos, with internal processes of creation and destruction set against the backdrop of the expanding universe. Not all galaxies are alike, however. As galaxies grew and interacted, they assumed diverse shapes and characters. Some became elegant spirals, others grew into sprawling ellipticals, and many smaller ones took on irregular, whimsical forms. In the grand cosmic menagerie, galaxies are as varied as the creatures in a primeval sea, spiraling, stretching,
colliding and twisting into different configurations. Their shapes are visible signposts of their histories. Spiral galaxies are the archetype we've already been exploring. They have pinwheel shapes, a flattened rotating disk with spiral arms, a central bulge, and often a bar of stars slicing through the bulge. Our Milky Way is one such barred spiral. Spirals are galaxies in their star-forming prime. Their arms, shining with young blue stars and dotted with pink emission nebulae, show that these galaxies still have plenty of gas to make new stars. The presence of dust in the disk creates dark filamentary lanes that outline the spiral structure when viewed face-on, and that give edge-on spirals a shadowy mid-plane. 2/3 of spirals, including the Milky Way, have a bar structure, which is thought to redistribute material and perhaps trigger star formation by funneling gas inward. Spiral arms can be tightly wound or more open and irregular. Some spirals, called grand design, have well-defined arms that can be traced almost a full circle around, while others have fragmentary arm segments. Regardless of exact form, the hallmark of a spiral is a mix of star ages, hot young stars in arms, and older stars in the bulge and extended disk, and an ongoing cycle of star birth. Elliptical galaxies have a very different look. They range from nearly perfect spheres to elongated football shapes. Ellipticals typically show no spiral structure, no disk, and crucially, almost no cool gas or dust. Thus, they lack the neon signs of star formation, no blue young star clusters or glowing nebulae. Instead, their light is dominated by older reddish stars. An elliptical galaxy often appears as a smooth gradient of light, brightest at the center and dimming uniformly outward, with little texture. The stars in ellipticals orbit in random directions, like bees in a swarm, unlike the coherent rotation in a spiral's disk. This suggests ellipticals likely formed by mergers of smaller systems. Imagine two spirals merging. Their ordered disks could be scrambled into one big cloud of stars, orbiting every which way. The largest galaxies in the universe are giant ellipticals found in cluster centers, which probably grew by consuming many smaller galaxies. Conversely, there are also tiny ellipticals, and dwarf spheroidals, only a bit bigger than globular clusters, often companions to larger galaxies. Without much gas, ellipticals have long since ceased meaningful star formation. They are largely in a passive, quietly shining state. Lenticular galaxies, SRO type, are something of a bridge between spirals and ellipticals. They have a disk, like spirals, often with a central bulge, but no spiral arms and very little gas or dust. A lenticular galaxy looks like a smooth disk or a bulge with a faint pancake around it. One might think of them as armless spirals or disk ellipticals. They likely form when a spiral galaxy uses up or loses its gas. For example, gas stripped by falling into a cluster or exhausted by star formation and feedback. The result is a galaxy that still rotates and has a disk structure, but no spark left to form new stars. Lenticulars often show dust lanes or rings, but no active HII regions. They tend to have intermediate colors, not as blue as star-forming spirals, not as red as ellipticals, although more toward the yellow due to aging stellar populations. If spirals are galaxies in their adulthood and ellipticals in old age, lenticulars are perhaps late middle age. The shape remains, but the youthful glow is gone. Irregular galaxies are those that defy the standard categories. They have no regular shape, neither a disk with arms nor a smooth ellipsoid. Many are small, dwarf irregulars, essentially blobs of stars and gas. They often contain significant amounts of gas and ongoing star formation, but in a haphazard pattern. The large and small Magellanic Clouds, visible to the naked eye from the southern hemisphere, are irregular dwarf galaxies orbiting the Milky Way. The Large Magellanic Cloud, LMC, actually has a bar and one spiral-like arm,
It's a magpie of a galaxy, part bar, part irregular disk. The small Magellanic Cloud is more chaotic, an amorphous sprinkle of stars with no obvious center. Such irregulars could be young galaxies that haven't settled into a definitive form, or were perhaps normal galaxies distorted by gravitational encounters. Some irregular shapes result from collisions. For instance, the aftermath of two galaxies grazing each other might be an irregular burst of stars. There are also ring galaxies and other peculiar forms, like the cartwheel galaxy's bullseye shape, usually arising from special interactions. Irregulars demonstrate that galaxy formation can be messy. They remind us that not every galaxy gets to be a neatly structured spiral or a smooth ellipse. Some are cosmic driftwood, fragments still finding their form, or scraps left over from bigger systems. In truth, many galaxies evolve from one type to another. A spiral can merge with another and become an elliptical. A tidal encounter can turn a spiral into a distorted irregular, perhaps temporarily, before it resettles. Two dwarfs colliding might spark a mini-spiral structure. The classification is a snapshot of a galaxy's visible state, but underlying that state is a story. Even so, Hubble's classic tuning fork diagram, spirals branching into barred and unbarred, lenticulars in the middle, ellipticals on the handle, remains a useful map of galaxy diversity. Each shape speaks to physical conditions. Spirals mean a spinning disk with ongoing star formation. Ellipticals mean a gravitationally relaxed system that likely experienced mergers and lacks fuel. Irregulars often mean either youth or disruption. Across the cosmos, we see that early on, many galaxies were irregular and clumpy. Over time, through mergers and accretion, some settled into spirals. Others, especially after big collisions, became ellipticals. Thus, the shapes we categorize are also stages in a galactic lifetime, or outcomes of galactic interactions. Different shapes also affect what life inside might be like. A planet in an elliptical galaxy's outskirts might have a night sky filled only with a gentle, diffuse glow. No grand Milky Way band, since the stars are more uniformly distributed. In a dwarf irregular, the sky might be relatively dark, except where a local pocket of star formation lights it up. In a spiral like ours, we enjoy the spectacular band of the Milky Way and rich constellations, a product of living in a structured, starry disk. Yet beneath these varied forms, galaxies share a fundamental role. They are star factories. No matter the shape, virtually every galaxy at some point converts gas into stars. This ongoing creation process is the heartbeat of a galaxy's life. Let us turn to that internal activity, common to all but the most dormant galaxies, the birth of stars within these island universes. Galaxies are cosmic furnaces where new stars are forged from interstellar gas. Deep within vast, cold molecular clouds in a galaxy's disk, gravity gathers pockets of gas until they ignite into stars. This happens continually in galaxies with available fuel. Spirals are especially prolific. They're giant molecular clouds, often tens or hundreds of light years across, and containing thousands of solar masses of molecular hydrogen, serve as nurseries for star clusters. Within such a cloud, small density enhancements draw in gas around them. As the gas compresses, it heats up. When a pocket, perhaps a few tens of times the sun's mass, collapses enough, the temperature and pressure at its core soar to the point that hydrogen nuclei begin to fuse into helium. At that moment, a star is born. A tiny thermonuclear furnace balancing gravity's inward pull with energy's outward push. The newborn star often emerges in a cluster with dozens or hundreds of siblings, all formed from the same cloud. The remaining gas may be blown away by the collective radiation and winds of those newborn stars, clearing out a bubble and leaving behind a shining cluster. Throughout a galaxy's spiral arms, this drama plays out in countless locales. For example, in our Milky Way, the Orion Nebula is one such stellar nursery. To the unaided eye, Orion's sword shows a faint fuzzy patch. Through a telescope, it's a glowing cavern of gas with a handful of massive young stars illuminating it. Those stars are mere infants, less than 1 million years old, and where we see the nebula's bright veil, many more protostars are likely gestating. The Orion Nebula is just one of many star-forming regions in our galaxy's Orion arm. Star formation rates vary. The Milky Way forms roughly 1 to 2 sun-mass stars per year. In fact, mostly lower-mass stars. The high-mass ones are rarer. Some galaxies, especially in earlier cosmic times or in violent starbursts, form stars much faster. There are galaxies observed, often due to collisions or mergers, forming perhaps 50 or 100 suns per year for short periods. We call these starburst galaxies. They blaze with the light of massive young stars and are often veiled in dust that those same stars later blow away. Conversely, small dwarf galaxies or massive gas-poor galaxies might only trickle out a star or two per year, or nearly none if they've lost their gas. Galaxies self-regulate this star formation to an extent. When many stars form at once, the first massive ones, O-type stars, emit intense ultraviolet radiation and charged particle winds. They heat and push on the surrounding gas. Shortly thereafter, within a few million years, some of those massive stars explode as supernovae, sending shockwaves through the molecular cloud. These effects can compress some parts of the cloud, triggering more stars in a chain reaction, but can also disperse other parts, shutting down further star formation in that region. In a spiral arm, one often sees this sequence like a ripple. Moving along the arm, there's a dust lane where gas is gathering, then bright emission nebula where stars have just formed, then star clusters with no nebulae, the gas blown away. It's a beautiful choreography. The galaxy's rotation and wave pattern orchestrate cloud collapse, and the newborn stars then orchestrate cloud destruction, limiting the yield. Over a galaxy's lifetime, this cycle steadily transforms gas into stars. In doing so, it also enriches the galaxy with heavy elements. The first generation of stars in a galaxy may have been born from nearly pristine hydrogen and helium left from the Big Bang. They lived and died, manufacturing heavier elements in their cores and in supernova explosions. Those metals, astronomers call all elements heavier than helium metals, mixed into the galaxy's gas. Later stars then formed from slightly enriched gas, and so on. Thus, as the galaxy ages, its gas and new stars contain higher fractions of elements like carbon, oxygen, silicon, iron, the very elements that make rocky planets and ultimately biology possible. Our Sun, born about 4.6 billion years ago, is metal-rich. About 2% of its mass is elements heavier than helium, evidence that it is a late-generation star. The earlier generations, now long gone, bequeathed the ingredients that went into the Sun and Earth. In this sense, galaxies are not just star factories, but also chemical factories, minting the periodic table as they go. The star formation process in galaxies will continue as long as there is cold gas to convert. But gas is a finite resource within a galaxy. It can be used up, or expelled, or locked in stars. Large galaxies can sustain moderate star formation for many billions of years, while small dwarfs may consume their gas quickly or have it stripped away by interactions. When we look at galaxies, their colors give away their star-forming status. Blue-tinted galaxies are actively forming stars. Short-lived blue stars tint the light, whereas yellow-red galaxies have little star formation, their light dominated by long-lived reddish stars. Many spirals have blue spiral arms but a yellowish bulge, indicating active star formation in the disk, but an older population in the core. Ellipticals are uniformly yellow-red, having long ago ceased making stars. Our Milky Way, with its mix of blue and white along the arms and a yellowish center, tells us it's still in business as a star factory, though not a starburst by any means. In its suburbs, like our Sun's vicinity, new stars form at a leisurely rate. In contrast, Consider a galaxy like M82, the Cigar Galaxy. It's undergoing a ferocious starburst likely triggered by interaction with its neighbor M81. In M82's core, stars are forming so rapidly that their combined winds and supernovae are blowing gas out of the galaxy in colossal superwinds, visible as filamentous outflows. It's a galaxy essentially heaving with the effort of birthing stars, and in doing so, it may be burning through its available gas in a cosmic blink, tens of millions of years, after which it will calm down, having spent its fuel. Thus, star formation is the heartbeat of a galaxy, sometimes steady, sometimes rapid and irregular. With each beat, new stars light up, and with them new possibilities, perhaps planetary systems, perhaps life. Every star we see in the night sky, aside from a few exceptions like supernovae, is evidence of this ongoing heartbeat. Our own existence is tied to it. The Sun is a product of the Milky Way's star-making abilities, and our planet's raw materials were forged in previous stars. One day, far in the future, the Milky Way and other galaxies will run low on gas. Star formation will slow to a trickle and eventually almost stop, as we'll discuss when we consider galaxies aging. But for now, in this epoch, the universe is still rich with galactic star factories. Each pinprick of light in a distant galaxy's photograph could be the home of millions of newly formed stars or stellar systems coming into being. In a very literal way, galaxies create the light that fills the universe. They are the engines turning dark, cold gas into brilliant starlight, generation after generation. They have been doing so since the cosmic dawn, and the cumulative light of all those newborn stars over the eons has gradually lifted the universe out of darkness. While stars are being born throughout a galaxy's disk, another drama is unfolding in the galaxy's core. At the center of most galaxies, as we noted, lies a supermassive black hole. In quiet times, this black hole is an invisible presence, detected only by its gravitational influence. But when it feeds, it can outshine the entire galaxy and radically affect its surroundings. The interplay between galaxies and their central black holes is a vital theme in cosmic evolution. We find that the mass of a central black hole is closely correlated with the mass of the galaxy's bulge in spirals, or overall stellar population in ellipticals. For instance, our Milky Way's black hole is about 0.01% of the galaxy's total stellar mass, and that fraction holds similarly for many others. This hints that the growth of black holes and the growth of galaxies went hand in hand. They know about each other. How could that be? The answer is feedback. When a galaxy's black hole accretes a lot of gas, it enters an active phase, becoming what we call an active galactic nucleus, AGN, which in extreme cases is a quasar. In this phase, the region around the black hole emits tremendous energy. Gas spiraling into the black hole forms a superheated accretion disk, shining across all wavelengths. Magnetic fields can tap into the rotational energy and funnel some plasma into enormous jets that shoot out of the galaxy's center at near light speed. Meanwhile, intense radiation pressure from the disk pushes outward on the surrounding gas. In effect, the feeding black hole blows a cosmic wind. This energy output can have profound effects on the galaxy. It can heat the interstellar gas or even expel significant portions of it from the galactic nucleus. If the black hole's output is powerful enough, it can sweep the galaxy's bulge nearly clean of the cold gas needed for star formation. This is one way star formation can be quenched in a massive galaxy. The quasar or AGN phase pumps energy into the galaxy and halts the supply of cool gas. The black hole's growth thus self-regulates. Once it becomes very luminous, it curtails further fuel from reaching it and also shuts down new star birth in the inner galaxy. This is why we don't see galaxies with ridiculously overmassive black holes compared to their size. The black hole will have effectively shut itself off by clearing out its vicinity. During the early active times, the galaxy black hole duo can be spectacular.
Quasars, seen in the young universe, were galaxies with incredibly bright cores, often disturbed or merging in appearance, suggesting that interactions funneled large amounts of gas to their centers, igniting both starbursts and quasar activity. These quasars likely blew out so much gas that their host galaxies soon ran out of fuel for both star formation and further black hole feeding. The quasar then faded, and the galaxy was left as a more passive, elliptical, or lenticular, full of old stars and with little gas, a veteran of a violent youth. Even in less extreme cases, we see AGN feedback at work. In clusters of galaxies, the central galaxy often shows signs that its black hole periodically inflates huge bubbles in the surrounding hot gas, observed as cavities in X-ray images. These bubbles rise and send gentle shockwaves into the cluster, preventing the hot gas from cooling down to form new stars. The black hole is effectively heating the environment enough to forestall a cascade of star formation that would otherwise happen as the cluster gas cooled. This phenomenon is observed in the Perseus cluster, Virgo cluster, and others, where beautiful filamentary structures in the hot gas correspond to past outbursts from the central AGN. Our own Milky Way's black hole, Sagittarius A, is currently faint. Its accretion disk is trickling only a bit of material. But not so long ago, cosmically speaking, it likely had a blazar-like episode. The Fermi bubbles, giant lobes of high-energy emission extending 50,000 light-years above and below the galactic center, are thought to be remnants of an outflow from Sagar A, perhaps a few million years ago. They testify that even a relatively small supermassive black hole can drive galaxy-scale phenomena when active. Thus, a galaxy's central black hole can be seen as a sort of power regulator. During formative times, it lights up and, through its winds and radiation, keeps the galaxy from overdoing star formation. Eventually, the galaxy and black hole reach an equilibrium. The black hole no longer has a deep reservoir of gas to feast on. Star formation slows down, and they settle into a quieter phase. When we observe a massive galaxy today that isn't forming stars, often we find a quiet but hefty black hole at the center, exactly as this co-evolution scenario predicts. It's remarkable. Something as tiny, in size, as a black hole's accretion disk can influence a whole galaxy tens of thousands of light-years across. It's like a gear in a clock, small but key to the whole mechanism. Black hole feedback provides a link between the very small, sub-parsec scales and the very large, galactic scales. Through it, the cosmos achieved a balance. Without it, models suggest galaxies would be too large and too blue, forming stars far longer than observed. With it, galaxies mature and stop growing after a point, aligning with what we see. In cosmic terms, we can imagine a kind of dialogue. As a galaxy's gas collected and stars formed, the central black hole grew. When the black hole became powerful, it said, "Enough," and blew out the remaining gas, both halting further star formation and starving itself. The galaxy, having been energetic and blue, became a more quiescent reddish system. We see the aftermath of this in the present universe's many red ellipticals and lenticulars. Our own galaxy hasn't undergone a major quenching. It's moderate in mass, but in about 4 billion years, when the Milky Way merges with Andromeda, our central black hole will likely feast on a lot of inflowing gas and could briefly become a quasar, perhaps helping to shape the merged galaxy that will result. Thus, the presence of central black holes and their ability to transform energy make them crucial to the story of galaxies. In youth, galaxies shine by the grace of star formation. In their energetic adolescence, some shine by the grace of an AGN. By old age, both processes wane, leaving a quietly shining population of stars and a dormant heavy heart at the center. Galaxies and their black holes are partners in this cosmic evolution, each influencing the other. Galaxies are not static islands. They are dynamic entities that are born, grow, and change over the vast history of the universe. From the first proto-galactic fragments after the Big Bang
to the majestic spirals and ellipticals we see around us today, galaxies have undergone significant evolution. They have accreted matter, collided and merged with one another, and transformed from active star-forming systems to, in many cases, quiescent assemblies of old stars. The story of a galaxy's life is written in its shape, its star content, and its motion. It's a biography spanning billions of years. In the beginning, as we recalled, the earliest galaxies formed when the universe was very young. They likely started as small clumps, dwarf galaxy-sized pieces drawn together by dark matter gravitational wells. These clumps were full of gas, which began forming the first stars. Early star formation might have been frantic, massive stars, short-lived, quickly enriching the surroundings with heavier elements upon exploding. Small clumps merged into bigger clumps. Through both chaotic mergers and smoother accretion of gas along filaments of the cosmic web, galaxies began to build up. Simulations of cosmic structure show that little galaxies, with masses perhaps 1,000,000 to 1,000,000,000 times that of the Sun, formed first and then congregated to form larger ones. This process is sometimes called hierarchical assembly, like small bricks assembling into bigger structures. Our Milky Way, for example, has cannibalized many smaller systems over time. It contains star streams and outer clusters that are the remnants of devoured dwarfs. Even now, it's shredding the Sagittarius dwarf spheroidal galaxy, adding those stars to its halo. In the past, it likely did this multiple times. This is how a large spiral can grow over billions of years. Galaxies also grew by accreting fresh gas from their surroundings. In the early universe, gas was more densely and readily available, and galaxies could draw in cold flows from intergalactic space, sustaining high star formation rates. Around 2 to 3 billion years after the Big Bang, roughly the peak of cosmic star formation, often called cosmic noon, many galaxies were in a veritable growth spurt, rapidly forming stars, growing their black holes, and often interacting with neighbors because the universe was smaller then. Everything was closer together. Collisions and mergers are a dramatic driver of galactic evolution. When two galaxies merge, their shapes are profoundly altered. If a small galaxy merges into a big one, a minor merger, the big one mostly keeps its identity. Perhaps the event thickens the big galaxy's disk, or flings some of the small galaxy's stars into the halo, or triggers some extra star formation. But when two comparably sized galaxies merge, a major merger, the result tends to be an elliptical galaxy. The violent relaxation of stars' orbits during the merger randomizes their motions, and any cold gas present can be either consumed in a burst of star formation or expelled by feedback. Thus, the end product is an elliptical with little gas. Major mergers also tend to grow the central black hole efficiently, since gas is funneled to the center, possibly igniting a quasar that then blows out the remaining gas. We believe many of today's giant ellipticals formed from such major mergers billions of years ago. Not every galaxy undergoes a major merger, though. The most massive ellipticals likely did, some multiple times. But many spirals, including perhaps our Milky Way, have had a relatively gentle history with only minor mergers. Such galaxies can retain their disk structure and continue forming stars gradually. The Milky Way has a mix of populations that tell its history. A thin disk of younger stars, a thicker disk of older stars, perhaps heated by past interactions, a halo of very old, metal-poor stars, some possibly from small galaxies it absorbed early on, and a central bulge that could be the result of an ancient merger or internal evolution of the disk through bar formation. Galactic evolution is also about the decline of available gas. Initially, galaxies had lots of fuel. By now, many have used much of it up or locked it in stars. As a rough trend, the universe's star formation rate has declined over the last 10 billion years. Large surveys of galaxies find that those in the past were, on average, forming stars at a higher rate than comparable galaxies today. This aging of galaxies means that the cosmic color palette
has shifted. In the past, galaxies were bluer, more hot young stars, whereas today, a larger fraction of galaxies are red and dead.
Environment plays a big role too. A galaxy in a rich cluster might have been quenched earlier. The cluster's hot gas can strip the galaxy's cold gas as it moves, a process called ram pressure stripping, and frequent encounters can stir up the galaxy and cause it to lose its orderly disk structure. Indeed, cluster galaxies are dominated by ellipticals and lenticulars, suggesting that many spirals that fell into clusters lost their gas and transformed. On the other hand, galaxies in lower density environments, small groups or voids, have fewer interactions and often retain their spiral structure and star-forming ability longer. Our local group, containing the Milky Way, Andromeda, Triangulum, and many dwarfs, is a fairly low-density environment. We have evidence that neither the Milky Way nor Andromeda has had a major merger in the last 9 to 10 billion years, allowing them to remain spiral galaxies. However, they are on course to merge with each other in about 4 to 5 billion years. When that happens, the result will likely be a more elliptical-like galaxy, sometimes nicknamed Milkomeda. Star formation may initially spike during the collision as gas clouds slam together, but eventually, much of the gas will either be used up or thrown out, and star formation will wind down. The merged galaxy will settle as a large, somewhat elliptical system with a very different night sky for any inhabitants. No clear disk band, perhaps just a diffuse glow of a central core, and an extended halo of stars. So the future of galaxies is, in a sense, written by their interactions. Over very long timescales, say 100 billion years or more, the continued merging of groups and clusters means many galaxies will coalesce into a few very large galaxies, especially as cosmic expansion drives distant ones out of reach. There's a concept that eventually gravitationally bound structures like our local group will merge into one giant galaxy. And beyond that, thanks to the accelerating expansion of the universe, that galaxy will be essentially alone, all other galaxies having receded beyond the observable horizon. But that far future scenario is speculative and far beyond any current age. In summary, the galaxy we see today is the product of billions of years of change. A spiral like the Milky Way was once smaller, likely a swarm of proto-galaxies coming together. It has grown by accretion and mergers, formed stars steadily, and will continue to change, especially with the impending Andromeda encounter. An elliptical in a cluster may have once been several disk galaxies that danced and combined. Even tiny dwarfs have stories. Some might be leftover building blocks that never made it into a larger structure, living fossils of the early cosmic times. Galaxies, therefore, have life cycles. They can be thought of in terms of birth, formation from primordial matter, growth, star formation and mergers, maturity, a steady state, often disk galaxies with ongoing star formation, and old age, exhaustion of gas, becoming passive. Not every galaxy neatly follows this, and some experience rebirth if new gas is acquired, but many do traverse from active to quiet. Our universe today contains galaxies in all these stages. When we look out in space, distance corresponds to looking back in time. Nearby, we see many ellipticals and gas-poor systems, galaxies that have largely completed their star-forming story. Far away, hence long ago, we see more irregular, clumpy galaxies furiously forming stars, the youth and adolescent stages. By combining those views, we piece together the saga of galactic evolution. Now imagine the large-scale arrangement of these galaxies. They are not scattered randomly like isolated birds. They congregate and form patterns on the grandest scales. Galaxies, along with galaxy clusters and superclusters, are woven into a cosmic web, a filamentary network that spans the observable universe. This is the imprint of the initial tiny density fluctuations from the Big Bang, amplified by gravity over billions of years. If we could zoom way out, far beyond our local group, beyond our local supercluster, we would see galaxies arranged in filaments and sheets, intersecting at dense nodes, clusters, with immense voids in between where few galaxies reside. This we call the cosmic web. It looks somewhat like a three-dimensional spiderweb or foam. Each filament might stretch hundreds of millions of light years and contain many groups and clusters of galaxies. At their intersections sit the richest clusters, like the Coma or Virgo clusters, teeming with thousands of galaxies. Between filaments are voids, huge cavities, 100 million light-years across or more, that have only a sprinkling of galaxies, truly cosmic emptiness. Our Milky Way inhabits a minor filament on the outskirts of the Virgo supercluster. Recently, astronomers gave our local supercluster the name Laniakea, meaning immense heaven in Hawaiian. We are pulled gently toward the dense center of Laniakea, the region of the Virgo cluster, but will likely never reach it due to the expansion of the universe acting on larger scales. The local group itself is a little cluster on a filament that extends out toward other nearby groups, like the M81 group and the Centaurus group, all on the boundary of the Virgo supercluster complex. This cosmic web is mapped by surveying galaxies and noting their 3D positions. One famous survey, the Sloan Digital Sky Survey, created maps with over 1 million galaxies, revealing an astonishing foamy structure. Long filaments and walls, like the Sloan Great Wall, a filament 1.4 billion light-years long, and huge voids such as the Bootes Void, where few galaxies dwell. It's fascinating to realize that on scales of billions of light-years, galaxies themselves are like atoms, gathering into these massive structures. Gravity is the sculptor of the cosmic web. Dark matter, which does not interact directly with light or normal matter except via gravity, began clumping first, forming a filamentary network under the influence of its own gravity. Normal matter, gas, fell into those dark matter structures. Wherever the dark matter density was highest at filament intersections, galaxies and clusters eventually formed from the cooling gas. Along the filaments, chains of galaxies emerged. In the voids, the paucity of matter left vast expanses nearly empty. One might imagine flying through the universe on these scales. For long stretches, you would traverse dark, relatively empty void, maybe passing an occasional lone galaxy or small group that inhabits a shallow density well. Then gradually, galaxies would appear more frequently, like approaching a metropolitan region. You might enter a filament. Around you, galaxies would pepper space in every direction, often clumped in groups. Further on, you could come upon a node, a cluster like Coma, where hundreds of galaxies swarm like bees in a hive, the ambient X-ray glow of hot gas suffusing the cluster. Exiting on another side, a filament might lead you onward to another cluster or spread out into a wall, a sheet-like arrangement dozens of megaparsecs wide, but relatively thin. To the human eye, of course, none of this structure is directly visible. We see it only by plotting galaxy positions. But an observer within a rich filament would see many galaxies in their night sky. Some might even be naked-eye bright if they're close enough, the way Andromeda is visible from Earth. In the heart of a cluster, the sky would be crowded with fuzzy glows of elliptical galaxies and maybe intense light from a central CD galaxy. In a void, the night sky might have far fewer galaxy smudges visible at all. An observer might not realize they're in a universe full of galaxies because most are so distant. This large-scale cosmic web continues to evolve. Over time, gravity will slowly pull filament galaxies toward the nodes, making clusters richer, while voids expand as matter drains out of them. However, the accelerating expansion of the universe, driven by dark energy, will counteract gravity on the larger scales, so the web might reach a sort of frozen configuration in the far future, where most structures don't grow much further because distant regions are receding too quickly to merge. Standing back, we can appreciate the cosmic web as the universe's grand design, the pattern underlying the distribution of galaxies. It's a bit poetic that galaxies, which themselves often look like webs of stars, spirals, are arranged in an actual web on a larger canvas. The phrase "connecting the dots" becomes literal. The galaxies outline the connections in this web. Now, an important component of that web and of galaxies' internal structure is something we mentioned earlier, but did not fully explore: dark matter. This is the unseen scaffolding that holds galaxies together and forms the framework of the cosmic web. It is the backbone of structure formation, yet it remains mysterious. We recall the evidence. Stars in the outer parts of spirals orbit unexpectedly fast. If visible matter were all there is, those outer stars should be moving slower, just as outer planets in the solar system orbit the sun more slowly, following Kepler's laws. Instead, galaxies' rotation curves flatten out. Stars far from the center orbit at roughly the same speed as those closer in. The logical conclusion is that there's much more mass spread out through the galaxy's halo than we can see, providing the extra gravity to keep those stars bound in fast orbits. Similarly, galaxies in clusters move as if there's far more mass in the cluster than the galaxies and hot gas alone account for. Thus arose the concept of dark matter halos. Each galaxy is enveloped in a halo of dark matter, extending well beyond the visible starry disk or body. In the Milky Way, for example, our visible disk is 100,000 light-years across, but our dark matter halo may span 600,000 plus light-years. Most of the Milky Way's mass, 85%, is in this halo. We don't see it. We only feel it gravitationally. What is dark matter? We don't fully know. It could be a new type of particle, often theorized as WIMPs, weakly interacting massive particles, or something like axions. We have evidence it's not made of ordinary atoms. Observations of the primordial elemental abundances and the cosmic microwave background imply normal matter is only 5% of the cosmic energy budget, while dark matter is 27%. Dark matter doesn't clump into stars or planets. If it did, we'd see those objects gravitationally or via blocked starlight. Instead, it seems to form diffuse halos. One striking illustration of dark matter's reality is the Bullet Cluster. Two galaxy clusters collided. The fiery crash of their normal matter, hot gas, can be seen in X-rays, slowed and squeezed at the center of the collision. But the galaxies themselves, mostly empty space, passed through and, here's the key, gravitational lensing maps show the main mass concentrations went through largely unimpeded, now ahead of the visible gas. The interpretation, the dark matter of each cluster, being collisionless, sailed through with the galaxies, whereas the gas, normal matter, interacted and was left behind. This separation of mass via lensing and normal matter via X-ray is a direct sign that the bulk of the mass is not in the gas or galaxies, but in dark halos. In galaxy formation, dark matter collapsed first into a web of filaments and halos. Without it, the gas alone, affected by pressure and radiation, would not have aggregated into structures as early as it did. Dark matter provided deep gravitational wells to collect gas and seed galaxy formation. Galaxies formed at the centers of these halos. Even now, galaxies live at the bottom of their dark matter halos, like luminous ships at anchor in an invisible harbor. As galaxies merge, their dark halos merge too, creating ever larger halos. In clusters, the dark matter halo of the cluster holds the member galaxies together. In our local group, the combined dark matter halo of the group might eventually encompass both the Milky Way and Andromeda, and all satellites into one enveloping structure. Yet, despite making up most of the matter, dark matter is elusive. It doesn't emit light, so we cannot see galaxy halos directly. We detect them via rotation curves, via galaxy motions and clusters, via gravitational lensing, distant galaxy images distorted by foreground mass. We build detectors deep underground, hoping a stray dark matter particle might collide with an atomic nucleus and give a tiny signal. So far, no definitive detection, but the hunt continues. Living inside a galaxy's dark matter halo is imperceptible. It's like living at the bottom of a deep ocean of gravity, but one that is calm and transparent. We feel only the net effect. For example, our solar system's motion around the Milky Way is faster than it would be from visible matter alone, thanks to dark matter. Perhaps occasionally, a dark matter particle zips through us without a trace. They are thought to interact so weakly that trillions pass through your body each second with nary a hint. Dark matter doesn't collide with itself in the normal sense, so halos tend to be puffed out and roughly spherical. Non-collisional matter doesn't flatten into disks. This is why the luminous part of a spiral is flat, but the dark halo is spherical and much larger. In summary, dark matter is the silent, invisible partner in the cosmic dance. It forms the scaffold on which galaxies are built and the glue that holds them together. Without it, the elegant spirals might fly apart, and the cosmic web itself would be a flimsy network rather than the solid frame of the universe. Having this unseen mass everywhere gives the universe a hidden richness. When we gaze at a beautiful galaxy, we should remind ourselves that what is visible is only a small fraction, like the tip of an iceberg gleaming above water, with the bulk submerged. When we see galaxies cluster, we must imagine the great clouds of dark matter encompassing them, overlapping, merging, anchoring the cluster's gravity. We often call galaxies island universes, but even islands are connected beneath the ocean's surface by the shape of the ocean floor. And so galaxies are connected by the dark matter landscape. They ride the currents and settle into the valleys carved by this invisible mass. In the present day, dark matter continues to influence how galaxies move within groups and clusters, and how those structures evolve under cosmic expansion. So we have galaxies luminous and dark, the interplay of shining stars and unseen mass. This interplay is on display when galaxies collide. We move now from the serene picture of a single galaxy to the dramatic scene of galaxies interacting. Sometimes, galaxies do not remain isolated. Gravity draws them together, and they can collide and merge. When galaxies collide, it's a slow-motion dance lasting hundreds of millions of years. Their stars are so sparsely distributed that the chance of star-to-star collision is extremely low. Most stars just sail past each other. But the galaxy's structures, their disks, arms, and gaseous contents, distort and intermingle under gravity's pull. The result can be both destructive and creative. Destructive in that the original orderly forms, like spiral arms, can be stretched into tidal tails or completely scrambled. Creative in that the collision often compresses gas and sparks tremendous bursts of star formation, and eventually forms a new, often larger galaxy. Picture two spiral galaxies drawing near. As their halos begin to overlap, each feels the other's gravity. The nearer edges of their disks tug on each other. Tidal forces draw out long streams of stars and gas from each galaxy, throwing them into intergalactic space. These are tidal tails, graceful arcs that can extend tens of thousands of light years beyond the merging galaxies. One famous example, the antennae galaxies, NGC 4038-4039 in Corvus. They are two merging spirals that have flung out long tails resembling an insect's antennae. Within their overlapping region, a frenzy of star formation is occurring, gleaming blue and pink in Hubble images. Over the next few 100 million years, those two cores will likely coalesce into one remnant galaxy, perhaps an elliptical, and the tails may fall back or drift away. During a collision, the stars mostly act like collisionless particles. They change trajectories due to the altered gravitational field, but rarely hit each other. Gas, however, behaves differently. Gas clouds do collide, shock, and collapse. So galaxy collisions often trigger starbursts as gas is funneled and compressed. In the antennae, for instance, hundreds of young star clusters, some superstar clusters far more massive than any in the Milky Way, have formed due to the encounter. In another well-known pair, M81 and M82, the larger galaxy M81 pulled gas out of M82, inducing a massive starburst in M82, hence its bright red core and superwind. Collisions can also feed central black holes. Perhaps merging two disks drives gas to the center to light up a quasar, as likely happened in many quasars' histories.
The shapes produced in collisions are diverse and often visually stunning. Aside from tidal tails, we see ring galaxies, like the Cartwheel Galaxy, where presumably a smaller galaxy punched through the center of a disk, sending outward a ripple of star formation that appears as a ring. Shell galaxies, ellipticals with faint concentric stellar shells, likely remnants of past mergers that settled in oscillating layers, and completely amorphous mergers where the entire system is a chaotic cloud of stars, eventually to relax into an elliptical.
Galactic collisions also can fling stars entirely out of galaxies, creating intergalactic stars. In clusters, we find a diffuse light between galaxies, partly from stars stripped during close encounters or mergers. In our local group, our Milky Way's interactions with dwarfs have left streams of stars, such as the Sagittarius stream, orbiting independently. Each collision is a one-time, unrepeatable event, with unique outcomes depending on masses, speeds, angles, and gas content. But generally, two similar mass disk galaxies merging will produce a more spheroidal galaxy and cease most star formation, especially if the merger uses up or expels the gas. Many scientists think that's why giant ellipticals in clusters exist. They are essentially merger pileups of many former spirals and dwarfs. From the perspective of any beings within a galaxy during a merger, the night sky would change over millions of years. They might see a faint smudge of the approaching galaxy grow larger and more detailed. Perhaps new bright stars and nebulae would appear as star formation ignites. Over long times, the constellations would be disturbed as star positions shifted gravitationally. If they survived to the end of the merger, which any individual star likely would, since direct stellar collisions are rare, they might find themselves in a very different type of galaxy, perhaps lacking a clear disk or patterns, and their sky now filled with a diffuse glow rather than a crisp Milky Way band. Destruction breeds creation. The old forms of galaxies are destroyed, but new arrangements of stars and new stars themselves are born. Tidal tails created by one merger might later condense into dwarf galaxies, essentially giving birth to new smaller galaxies as byproducts of a big merger. In fact, some astronomers suspect that certain dwarf galaxies around giants could be tidal dwarf galaxies from past interactions rather than primordial objects. Over time, most galaxies will participate in at least minor mergers. Our Milky Way is currently cannibalizing some dwarfs as noted, and in the future will engage in a major merger with Andromeda. In about 4 billion years, Andromeda's disk will start to distort the Milky Ways, and by 5 to 7 billion years, they will likely coalesce into a single elliptical-like system, nicknamed Milkomeda. This merged galaxy may then eventually gather the other local group members. Farther down the line, billions of years later, it might even fall into the Virgo cluster, though cosmic expansion might prevent that. Nothing is truly static. Collisions highlight another feature. Galaxies contain a lot of empty space relative to their size. If two spirals were shrunk to the size of two frisbees and thrown at each other, one might expect a smash. But in space, even when their disks overlap, stars mostly miss each other because of scale. The frisbees in this analogy are loaded with grain of sand stars inches apart. Two thrown frisbees would result in many sand grains colliding. But in galaxies, stars are like grains, perhaps miles apart on those frisbees. Not a perfect analogy, but it gives a sense of the sparseness. Ultimately, colliding galaxies tend toward equilibrium. Eventually, the gravitational chaos settles into a new, stable shape, often an elliptical. The wild star formation consumes gas and then peters out. The stellar orbits randomize and the system becomes dynamically relaxed. What was two lively spirals becomes one big, perhaps complacent, elliptical. Destruction creates beauty. The antennae-like tails, the rings, the burst of nebulae, all transient loveliness in the cosmic theatre. Eventually that fades, and a more subdued form remains, carrying in its diffuse light the mixed heritage of its progenitors. We see many ellipticals with faint tidal features or multiple nuclei or other signs that they formed from mergers, ghosts of their past lives etched in starlight. Thus, galaxies not only live, they can also reproduce in a sense, two become one, spawning perhaps smaller offshoots in the process, like tidal dwarfs. The number of galaxies can change with time, in regions like clusters. Initially, many moderate galaxies merged into fewer large ones, galactic cannibalism. In our local group, the number of substantial galaxies will reduce from two major, Milky Way, Andromeda, to one. But the combined light and mass remain roughly the same, minus whatever is ejected into intergalactic space. Having considered this tumult of collisions and growth, let us return to a familiar vantage. Our own galaxy, the Milky Way, which has thus far led a somewhat quieter life, allowing life to arise here. We have seen how galaxies in general work. Now we focus on the specific characteristics of the one we call home. The Milky Way is a barred spiral galaxy with a disk over 100,000 light-years in diameter. It has a central bulge of stars, about 10,000 light-years thick, and a bar of stars about 25,000 light-years long crossing the bulge. From the ends of this bar emanate the spiral arms. At least two major arms, Scutum Centaurus and Perseus, and several smaller segments or spurs, like the Orion arm where our Sun resides. Our galaxy's total stellar mass is on the order of 100 billion suns. It's accompanied by a retinue of over 50 satellite galaxies, mostly dwarfs, and is itself part of the local group with Andromeda and others. We experience the Milky Way from within. On a clear night in a dark location, we see it as a milky band arching across the sky. That is our edge-on view of the dense galactic disk. Through telescopes, this band breaks into countless faint stars and dark dust lanes. Toward the constellation, Sagittarius lies the galactic center, about 27,000 light-years away, behind thick dust clouds that hide the nucleus in visible light. In that direction, the Milky Way band is widest and brightest because we are looking toward the packed central bulge and along several spiral arms overlapping. At the center, beyond visual reach, sits the Milky Way's supermassive black hole, Sagittarius A. We have mapped stars orbiting extremely fast there, up to a few thousand km, indicating a mass of 4 million suns in a volume no larger than our solar system, hence a black hole. Currently, SGR-A is quiet. It's not actively accreting much gas, so it's effectively dark. If it were feeding, we'd detect strong radiation from that region, X-rays, etc. As mentioned, evidence of past activity, the Fermi bubbles, suggests it's had active episodes. Surrounding the nucleus is the bulge, a roughly spheroidal swarm of older stars, many red giants among them. The bulge has a higher proportion of old metal-rich stars, and likely also contains the bar structure. The bar is basically a stretched bulge. Our vantage point, offset from the center, means we see the bulge as a widening of the Milky Way's central glow. The disk of the Milky Way is the dominant feature. It is fairly thin, about 1,000 light-years thick in the star-forming regions, thicker in older stars. It contains most of the gas, in forms ranging from hot ionized regions to cold molecular clouds and dust. Our Sun orbits within this disk, currently about 25 pc, 80 light-years, above the midplane. We bob up and down through the plane as we orbit. The solar system completes one orbit around the center every 240 million years, sometimes called a galactic year. We've likely done about 20 orbits since the Sun's formation, meaning the Sun has been in various parts of the Milky Way's arms and spaces between arms over time. Our galaxy's spiral structure has been discerned by carefully mapping concentrations of gas via radio observations of hydrogen and carbon monoxide and young star clusters. We know that it has a barred center from infrared surveys like COBE and Spitzer that penetrate dust. The major arms are the Perseus arm, outside our orbit, and the Scutum Centaurus arm, inside our orbit, wrapping around the galaxy. The Sun lies in a smaller spur called the Orion Cygnus arm, or local arm. This local spur connects the major arms and contains the Orion Nebula, the Carina Nebula, and other nearby star-forming regions. Our galaxy is currently forming stars at a moderate clip, a few M per year, mainly in the spiral arms. Notable star formation complexes include those in Carina, Scutum, Sagittarius, all toward the inner galaxy, and the Perseus arm, farther out. We also have ongoing star formation in the molecular ring about 4 kpc, 13,000 Li, from the center, which might be related to the bar's dynamics funneling gas there. The Milky Way's halo is a roughly spherical zone surrounding the disk and bulge. In this halo are the oldest known stars of our galaxy, some nearly as old as the universe, found in globular clusters and as solitary halo stars passing through. We have observed about 150–160 globular clusters orbiting the Milky Way. These clusters are dense, gravitationally bound spheres of ancient stars, typically 12 billion years old or more. They reside mostly in the halo, on random elliptical orbits, tilted at various angles to the disk. Harlow Shapley in the 1910s used the distribution of globular clusters. They form a roughly spherical cloud centered on the galactic center, to infer the Sun's offset position and the size of the Milky Way, one of the first steps in understanding our galaxy's true scale. The halo also contains the dark matter halo mass. The stellar halo, visible stars, is tiny compared to the dark halo, but it's our tracer of the halo's extent. Many halo stars and globulars have very low metallicity, few heavy elements, indicating they formed when the galaxy, or its precursor fragments, was very young and mostly unpolluted by supernovae. Some might even predate the Milky Way, having formed in smaller progenitor galaxies that later merged into the Milky Way. The Milky Way sits in a neighborhood with dozens of other galaxies, the local group. Dominating our local group are the Milky Way and the Andromeda galaxy, M31. Andromeda, slightly more massive and about 2.5 million light-years away, is a spiral galaxy quite similar in structure to our own, barred as well, with a vast swarm of satellites. The third largest member is the Triangulum galaxy, M33, a smaller spiral, maybe 1/5 the mass of Andromeda, which might be a satellite of M31 or an independent member. Beyond these 3 spirals, the rest of the local group is composed of dwarf galaxies. Most of these are satellites of either the Milky Way or Andromeda, and a few lie in between. The Milky Way's notable satellites include the large and small Magellanic Clouds, 2 irregular dwarf galaxies visible prominently from the southern hemisphere. They contain active star-forming regions, like the Tarantula Nebula in the LMC, the most luminous star-forming region in the local group, and are interacting with our Milky Way. A stream of gas, the Magellanic Stream, stretches from them, drawn out by tidal forces. The LMC and SMC orbit the Milky Way at distances of 50 to 60 kpc, 160,000, 200,000 Li. Over the next few billion years, they may either merge with our galaxy or possibly be stripped apart. Other Milky Way satellites include dwarf spheroidal galaxies such as Sagittarius, Draco, Ursa Minor, Carina, Sextans, Sculptor, Fornax, and many discovered more recently,
like Tucana 2, Reticulum 2, etc., found in data from surveys such as SDSS and DES. These are generally tiny, faint galaxies. Some have only a few million stars, and they often appear as barely detectable smudges of light in telescopes. They have little to no gas and are supported more by random motions of stars, not rotation, analogous to miniature ellipticals. They tend to reside within a few 100,000 light-years of the Milky Way, and some, like Sagittarius Dwarf, are actually in the process of being tidally disrupted by it. Indeed, the Sagittarius Dwarf, discovered in 1994, is wrapping around the Milky Way in a stream of stars, evidence caught in stellar surveys as an overdensity of certain tracer stars. Andromeda likewise has its cohort of dwarfs, like M32 and M110, two dwarf ellipticals right next to its disk, visible even in early photos by Messier, and many dwarfs discovered around it, such as Andromeda 1 to 2, etc., and the recent surprise of a thin plane of satellite galaxies seemingly aligned around M31. Triangulum, M33, is smaller and has only a couple of tiny companions known. The local group as a whole is about 3 million parsecs, 10 million light-years, across, and is gravitationally bound. The Milky Way and Andromeda are approaching each other. 110 km/s inward motion on top of some transverse motion. The group itself is moving toward the Virgo cluster, but likely will not reach it due to cosmic expansion. The local group's center of mass lies somewhere between the Milky Way and Andromeda. These two giants orbit that center and each other slowly. This little family of galaxies drifts together in space. Inside it, galaxies can affect each other. Our Milky Way is clearly affecting and consuming some of its dwarfs. Andromeda has likely swallowed some of its own. Its halo contains many streams indicative of past mergers. Eventually, as noted, the two big ones will merge. Effectively, the local group will condense into one galaxy containing most of the stars of the current group. The local group sits at the edge of the Virgo supercluster. Just beyond our group, about 15 million light-years away, lie small groups like the M81 group, around the spiral M81 in Ursa Major, and the Centaurus A M83 group, around Centaurus A, a peculiar elliptical, and M83, a spiral. Further out, how 50 to 60 million Li, is the Virgo cluster itself, a massive cluster of 2,000 galaxies. Our local group is being gently tugged toward Virgo, the Great Attractor region, which also includes the Centaurus cluster, Norma cluster, etc. But we are not part of Virgo. Rather, the local group is like a little outlying suburb of that enormous cluster complex. The environment of the local group, relatively isolated in a cosmic filament, has allowed the Milky Way and Andromeda to retain their gas and spiral forms longer than they might have in a dense cluster environment. It's a quieter corner of the universe. Now, not all galaxies in the cosmos are large like the Milky Way or Andromeda. In fact, by number, dwarf galaxies dominate. These are galaxies with much smaller masses and luminosities, often just a few million to a few 100 million stars instead of billions. Some dwarfs are irregular, like the Magellanic Clouds. Others are spheroidal or elliptical. Dwarfs are the building blocks that, assembled together, formed bigger galaxies. Many dwarfs also persist as separate entities, especially around bigger galaxies as satellites, or in isolation in voids. Dwarf galaxies are intriguing. Because of their low gravity, they're susceptible to having gas stripped or blown out. Many dwarf spheroidals around the Milky Way have no gas at all. Likely, the Milky Way's tides or radiation long ago removed it, or internal supernovae winds expelled it. These dwarfs consist mostly of old stars and are very faint. They are also extremely dark matter dominated. For example, the Draco dwarf contains only a few million solar masses of stars, but perhaps tens of millions of solar masses of dark matter. Its stars move as if a lot of unseen mass is present. making it effectively a lump of dark matter with a frosting of stars. This makes dwarfs excellent test beds for dark matter theories on small scales. Some dwarfs are more like surviving siblings of big galaxies, having converted only a small portion of their gas into stars and hanging onto their gas reservoirs for a long time. The Magellanic Clouds, for instance, still have plenty of gas and active star formation. The LMC even has its own satellites, a mini-system. In the early universe, many dwarfs probably merged into larger systems, but those that didn't can be seen as fossils of that time. We might liken dwarfs to cosmic plankton, tiny, numerous, easily influenced by currents, tidal forces from larger galaxies, yet absolutely essential in the food chain of cosmic structure. Without dwarf mergers, many larger galaxies would not have grown so massive. Without dwarf galaxies as satellites, big galaxies wouldn't have some of their halo stars, captured from dwarfs, or their extended globular clusters. Some globulars could be the nuclei of dwarfs that were consumed. The space between galaxy clusters is filled with isolated dwarf galaxies too, some in the process of falling into groups clusters for the first time. These tend to be gas-rich because nothing removed their gas yet, and are forming stars slowly. Over time, they might either form a few more stars and remain small, or eventually fall into a cluster and get stripped to become an ultra-diffuse cluster member. One fascinating aspect: dwarfs can have difficulty hanging on to not just gas, but also metals. When a star in a tiny galaxy explodes as a supernova, the blast can accelerate gas past the dwarf's escape velocity, blowing heavy elements out into intergalactic space. So many dwarf galaxies have much lower metallicity than larger ones of similar age. They lost more of the metals their stars produced. In this way, dwarfs pollute the intergalactic medium, enriching the cosmic environment with elements that later might be incorporated into other galaxies or proto-galaxies. Thus, dwarfs, though small, play a role in cosmic chemical evolution disproportionate to their size. In our local group, the ongoing accretion of dwarfs by the Milky Way and Andromeda is an example of the galactic cannibalism that likely happened frequently in the past. The halos of large galaxies are essentially graveyards of smaller ones, strewn with their tidally torn debris. We see these as stellar streams in our halo, like the Sagittarius stream, GD1, PAL5 stream, etc. Andromeda too is laced with streams. Each is the remains of a dwarf galaxy or globular cluster consumed and assimilated. Over time, those streams will phase mix into the halo, becoming indistinguishable smears of stars, adding to the smooth halo light. While many dwarfs live as satellites, some are relatively isolated. For instance, the tiny galaxy Wolf-Lundmark Melotte, WLM, on the outskirts of the local group a 3 million Li away, is a dwarf irregular that has led a solitary life, slowly forming stars, barely interacting with bigger neighbors. It gives us a glimpse of how a very small galaxy evolves on its own. In sum, dwarf galaxies are crucial pieces of the cosmic puzzle. They were the seeds of larger galaxies and remain the most common galaxy type by number. Often overlooked due to their faintness, they carry important clues about the early universe, the low mass end of galaxy formation, and the nature of dark matter through their extreme mass-to-light ratios. We, within the Milky Way, are currently treating our dwarf neighbors in a mixed way. Some we nurture. The Magellanic Clouds are being drawn in and likely eventually will mix with us, but for now, they're triggered to form stars maybe by our tidal influence. Some we have torn apart, Sagittarius, and others orbit peacefully for now, Fornax Dwarf, etc., which still have some old stars and even globular clusters of their own. In a few billion years, if any distant future astronomers compile a census, they might find that what was once dozens of dwarfs became just stellar streams in an enlarged Milky Way halo. Now, galaxies not only consume matter and form stars, they also breathe, in a sense. Massive stars and active nuclei can drive galactic winds, outflows of gas that extend far beyond a galaxy's main body. Through these winds, galaxies can expel some of their content into intergalactic space, influencing their surroundings and regulating their own growth. In a star-forming galaxy, especially one experiencing a starburst, the combined effect of many supernovae and stellar winds can create a superwind. We see a dramatic example in the Cigar Galaxy, M82, which we encountered as a starburst triggered by interaction. M82 shows twin reddish plumes of gas billowing out perpendicular to its disk. This is a galactic wind. What's happening is that thousands of supernovae from the central starburst have heated and propelled gas outward. This gas, a mix of hot plasma and cooler entrained material, is leaving the galaxy's gravitational grasp. Some of it might fall back later, but much may escape into intergalactic space. Along with gas, metals, carbon, oxygen, etc., are carried out, meaning the galaxy enriches its environment. Galactic winds are crucial in galaxy evolution. They can remove gas that would otherwise form more stars, effectively putting the brakes on star formation, especially in smaller galaxies where the gravity is weaker. It's easier for a wind to evacuate a dwarf galaxy than a giant one. This is one reason dwarfs often have low star formation rates or shut off early. They lost their gas to winds. Even in large galaxies, winds, often aided by an active black hole's energy output, can clear out the central regions and halt star formation there, leading to the kind of gas-free bulges we observe. Winds also disperse the ashes of stellar furnaces, the heavy elements. The intergalactic medium in galaxy clusters is observed to be enriched with iron and other metals, likely supplied by winds from member galaxies' past starbursts and outflows from active nuclei. In the early universe, before clusters existed, proto-galaxies likely blew metals into intergalactic space, seeding the raw primordial gas with heavier elements. So galactic winds are like the breath of galaxies that pollinates the cosmos. Another aspect is that winds can interact with a galaxy's surroundings. In a cluster environment, one galaxy's wind might slam into the intracluster medium, producing shocks. We sometimes observe X-ray or radio features in clusters that correspond to past winds or jets. In the cosmic web filaments, winds from galaxies can spread metals along the filament, enriching gas that might later fall into other galaxies downstream. Our Milky Way has modest outflow activity now, but evidence suggests that it too has or had a galactic wind. Aside from the Fermi bubbles produced by past AGN activity, there's also a structure called the Galactic Chimney, or the Northern Chimney, a region above the disk where hot gas from widespread star formation in the past may have vented out of the disk. The halo of our galaxy contains traces of elements that likely came from past outflows. When enough gas is expelled, it can eventually cool and rain back down, a process called a galactic fountain. In some spirals, localized starbursts blow gas out, which later falls back in a gentle drizzle elsewhere, redistributing metals across the disk. The Milky Way's halo gas, detected in UV absorption lines, might partly be fuel that is slowly cooling and returning, or fresh infall from outside, probably a mix of both. All this breathing, outflow and inflow is part of the self-regulation of galaxies. Too much star formation? Winds blow out gas, slowing things. Later, if the galaxy is quiet, it might accrete more gas again from its surroundings, or the expelled gas might cool and fall back, allowing a new cycle of star formation. This feedback loop helps explain why galaxies don't use all their gas at once in a single burst, except perhaps extreme starbursts, which essentially do and then become dormant. In the big picture, galactic winds are one of the mechanisms linking the small scale of stars to the large scale of galaxy groups. They enable material and energy exchange between a galaxy and the intergalactic medium. Through winds, galaxies essentially communicate with the universe, sending out signals in the form of enriched gas and receiving, in turn, sometimes pristine gas later. So we have painted a portrait of a galaxy's internal life.
Stars forming and dying, black holes growing and regulating, gas being cycled and sometimes expelled. Galaxies are not closed ecosystems. They interact with their environment gravitationally and through these winds and outflows. Let us now step back to a more distant time, when galaxies and black holes were in their most exuberant phases. In the young universe, quasars and active galactic nuclei were far more common. A quasar, short for quasi-stellar object, is the extremely luminous core of an active galaxy, powered by rapid accretion onto a supermassive black hole. During the peak quasar epoch, roughly 10 to 12 billion years ago, many forming galaxies shone as intensely bright quasars, visible clear across the universe. Quasars are among the brightest objects in existence. Some radiate the power of trillions of suns from a region no larger than our solar system. The nearest quasar to us, for instance, is dozens of times farther than Andromeda, yet can be seen in modest telescopes as a faint star-like point. And more distant quasars, whose light began traveling to us when the universe was only a billion years old, are detectable because of that immense luminosity. These beacons signaled that massive black holes were rapidly devouring matter in early galaxies. Often, quasars are associated with disturbed, merging galaxies, hinting that a collision funneled gas into the nucleus. The incredible output of a quasar is multi-wavelength, visible light, ultraviolet, X-rays, infrared. The accretion disk emits a broad spectrum. Quasars also often produce jets that emit radio waves. Some of the first quasars were discovered via radio surveys. Observationally, a quasar appears star-like, hence quasi-stellar, because at tens of billions of light-years, the host galaxy's extended light is too faint to see. Only the brilliant core registers. It was through spectroscopy that astronomers in the 1960s realized these star-like objects had enormous redshifts, implying they were incredibly distant and thus incredibly luminous to be visible at all. That realization expanded our understanding of both galaxies and black holes, revealing that some galaxies in the distant past went through a quasar phase. As the universe aged, quasars became rarer. Why? Likely because the fuel supply at galactic centers became less abundant once major mergers became less frequent and most central black holes had reached a satiation point. The quasars we do see nearby are relatively less powerful AGN, or are cases of a late accretion event. For instance, a galaxy might reignite its nucleus by swallowing a gas-rich dwarf. Active galaxies come in various forms: quasars and Seyfert galaxies, active nuclei in spiral galaxies, radio galaxies, ellipticals with huge jets and lobes of radio emission, blazars, AGNs whose jets point directly at us, making them appear especially variable and bright in high-energy output. All are manifestations of the same engine, accretion onto a supermassive black hole. The differences are often in orientation and scale. A unified model suggests that a quasar and a radio galaxy could be the same type of object viewed from different angles, with or without seeing the jet, etc. These active phases likely have finite duration, maybe a few million to tens of millions of years for a quasar-level episode. Some galaxies may have undergone multiple episodes if conditions allowed, e.g. periodic infall of fresh gas. In fact, our Milky Way's center might have flickered as a weak quasar for short spurts when it had access to enough gas. The evidence of past activity hints at that. What do quasars mean for galaxy evolution? As discussed, they are an extreme form of AGN feedback. A powerful quasar can blow out the bulk of a galaxy's gas, effectively truncating star formation. So quasars likely mark the end of growth spurt for their host galaxies, a sign that the galaxy has accumulated a large black hole and is now clearing itself out. It's like a candle flaring brilliantly just before it exhausts its fuel. From a cosmological standpoint, quasars are useful beacons for studying the early universe. Their light, traveling billions of years, carries information about the intergalactic medium it passed through. We see absorption lines from intervening gas clouds in quasar spectra, which has told us about the distribution of matter in the young universe, the rise of cosmic metals, and the epoch of rionization, the tail end of the Dark Ages, when early light sources rionized hydrogen. The farthest known quasars, with redshifts around 7.5, universe age, 700 million years, challenge our understanding. They have black holes, 1 billion solar masses already, meaning black holes and galaxies can grow very quickly in the right circumstances, probably via rapid, direct collapse of gas and early mergers. As we contemplate other galaxies, especially those outside our immediate cosmic neighborhood, we might see many that no longer have quasars, but carry evidence that they once did. Perhaps an oddly low gas content, or an overmassive black hole relative to their current size. The imprint of that active past can linger. We, collectively as a cosmic memory, look back at the epoch of quasars as a time when the universe itself was in a tumultuous youth. Galaxies were colliding frequently, star formation rates were high, and central black holes were feasting. It was a mysterious, energetic, almost violent phase, yet also one that seeded the calmer cosmos we inhabit now. Quasars, in their brilliance, helped bring an end to the era of universal star frenzy and paved the way for the mature galaxies of today. Now we shift focus to how we know all this, how we observe galaxies across light and time. We humans, tiny creatures within one galaxy, have managed to build instruments that extend our senses to the edges of the cosmos. Through them, we piece together the life stories of galaxies. When we look at a galaxy, we are also looking into the past. Light takes time to travel. When you see Andromeda tonight, you view it as it was, quite 2.5 million years ago, when early hominins on Earth might have just begun using stone tools. The farthest galaxies we observe appear to us as they were mere hundreds of millions of years after the Big Bang. Thus, astronomy is like time travel by vision. By observing more and more distant galaxies, we essentially watch the cosmic movie in reverse. Nearby galaxies show the present frame, far galaxies show earlier frames. Our primary tools are telescopes that capture different wavelengths of light because galaxies emit or absorb across the spectrum. With optical telescopes like the Hubble Space Telescope or large ground-based observatories, we see the stars and star clusters, the shapes of galaxies, and sites of active star formation outlined in high emission. Infrared telescopes, like the Spitzer Space Telescope and now the James Webb Space Telescope, can see through dust to reveal stars and structures hidden in dusty regions, such as the Milky Way's center or star-forming molecular clouds. Infrared also picks up the glow of cooler, older stars that dominate galaxies like ellipticals, and it can detect redshifted light from very distant galaxies that has been stretched into infrared wavelengths by the expansion of the universe. Ultraviolet telescopes, like Galactic, highlight the most massive young stars and thus pinpoint where star formation is happening in a galaxy. X-ray observatories, Chandra, XMM Newton, see the high-energy processes, accreting black holes in AGN, shining in X-rays, and hot gas in clusters or galaxies. Radio telescopes map cold gas, notably the 21 cm line of neutral hydrogen, and also synchrotron emission from relativistic electrons in magnetic fields, tracing things like jets and supernova remnants. Each wavelength adds a layer to our understanding. For example, optical images of a spiral might show a pretty pattern of arms and some dark dust lanes, but a radio map of the same galaxy might reveal huge spiral extensions of hydrogen gas beyond the visible disk, perhaps warps or streams connecting to neighbors. Ultraviolet might show that the outer disk has clumps of young stars beyond where optical light seemingly ends. Infrared might unveil a barred structure in the core invisible in optical due to dust. It's like examining an organism under different types of light to see different components, bones with X-rays, heat with infrared, etc. One of the most powerful techniques in observing galaxies has been spectroscopy.
By dispersing a galaxy's light through a prism or grating, we see spectral lines, signatures of elements in stars or gas. From these, we measure velocities via Doppler shifts. We can thus gauge how fast parts of a galaxy rotate, leading to those rotation curves for dark matter studies. We can measure how fast galaxies themselves move relative to us, the redshift, which in the context of universal expansion tells us their distance. Spectra also reveal chemical abundances, e.g., the strength of certain lines indicates how much heavy elements the gas has. Thus we know, for instance, that dwarf galaxies typically have low metallicities compared to large galaxies. Combining imaging and spectroscopy across wavelengths, we have developed a fairly complete medical chart for galaxies. Their masses, their compositions, their star formation rates, their temperatures, color indices or spectra, their environments, and so forth. With that, we infer their histories. We owe much to telescopes like Hubble for visualizing the distant universe. The Hubble Deep Field in 1995, for example, was a long exposure on a tiny patch of apparently empty sky. The resulting image revealed thousands of faraway galaxies of all shapes and colors. A cosmic scrapbook of galaxy evolution. We saw tiny blue galaxies, probably distant irregulars or spirals in their star-forming prime. Larger reddish galaxies, perhaps already formed ellipticals in the background. Odd interacting pairs, chain-like clumpy galaxies, etc. This one picture revolutionized our appreciation of how many galaxies are out there, an estimated hundreds of billions in the observable universe, and gave a snapshot of galaxies billions of years ago. Recently, the James Webb Space Telescope, with its infrared vision, has begun to see even further back, identifying candidate galaxies at redshifts above 10, within 500 million years of the Big Bang. These are extremely faint, and often just red smudges or dots even to Webb. But their existence is exciting. They might be among the first generations of larger structures. Some have unusually high brightness or masses, prompting astronomers to recheck how quickly galaxies could have grown. Webb's early data hints that some galaxies got big surprisingly fast, which could challenge or refine our models of early star formation and dark matter collapse. Gravitational lensing has been another boon. Massive clusters can magnify and stretch the images of background galaxies behind them. With lensing, we have observed galaxies that would normally be too faint or small. For example, the galaxy dubbed Earendel, after a Tolkienian name meaning morning star, was detected by Webb. It's a highly magnified image of what might be a single star or star cluster in a galaxy 12.9 billion years in the past, magnified by a factor of thousands by a foreground cluster's lensing. Likewise, Hubble found the most distant galaxy known, GNZ 11 at redshift HUT 11, via deep field imaging and spectroscopic confirmation, capturing it thanks to its relative brightness, possibly enhanced by lensing or an inherent starburst. The observable universe is limited, but within that horizon, our instruments have reached remarkably far. The edge of what we can see is basically defined by the faint afterglow of the Big Bang, the cosmic microwave background, at redshift L1100. We cannot see galaxies past a certain redshift because there were none before a certain time, and because beyond a certain point, space expansion carries them away, such that their light hasn't reached us yet. What does the edge of visibility look like? As discussed, the farthest confirmed galaxies and quasars are around redshift 7 to 10, the universe 500 million to 700 million years old. Beyond that, we expect only proto-galactic fragments and the first light of stars reionizing the universe. There's a race on. Can JWST or future extremely large telescopes detect galaxies at redshift 15, 20? Possibly not bright galaxies, but maybe hints of star clusters or supernovae in that era via some serendipitous events. With each improvement in technology, larger telescopes, better detectors, new wavelength windows opened, we peel another layer of the universe's story. In the coming decades,
New observatories like the Rubin Observatory for optical surveys, the Roman Space Telescope, infrared wide field, great for finding early galaxies via lensing surveys. ELTs, extremely large telescopes, 30-40 mils class on the ground. And maybe one day missions like LUVOIR or HABEX could allow us to map out even more of the universe's galaxies and even take spectra of extremely distant faint smudges to definitively gauge their ages and compositions. In doing this, we must preserve humility. We see snapshots, and from snapshots, we reconstruct narratives. Sometimes a galaxy can trick us. Two galaxies superposed can look like one odd one, or a transient event can make a galaxy seem more luminous. But overall, the consistency of evidence gives us confidence in the broad strokes of cosmic history we've outlined. Our viewpoint from inside the Milky Way is both a blessing and a curse. Curse in that dust and our position make mapping our own galaxy challenging. We did not even know the Milky Way's spiral structure well until the mid-20th century. But blessing in that, we have a ringside seat to a galaxy's internal details. We can study individual stars in galaxies, at least our own and near neighbors, which is impossible in far galaxies. Thus, we use the Milky Way as a template to understand certain fine-grained physics and external galaxies to place the Milky Way in context. We see that our galaxy is just one of a vast population, typical in some ways, perhaps a bit above average in mass, but certainly not unique except to us. Using light as our messenger and time machine, we have observed galaxies through 13+ billion years of cosmic evolution. We've catalogued their variety and, in doing so, discovered our own origins. Every image of a distant galaxy is also an image of what our own might have looked like long before the Earth existed. In that sense, observing galaxies is a form of introspection for the universe. It is the cosmos looking back at itself through us, examining different chapters of its autobiography. As we push the boundaries of observation, we approach the edge of the observable universe. This is the maximum distance from which light has had time to reach us since the Big Bang. It's about 46 billion light years away. Not 13.8 billion, because as light traveled, the universe expanded. At that horizon, galaxies, or proto-galaxies, are seen at the very dawn of cosmic time, if at all. Beyond it, light from any object is still en route and won't arrive until the future, or, if beyond the event horizon set by accelerated expansion, perhaps never. Already, at redshifts around 1011, we observe galaxies that are basically at the limit of current capabilities. They appear as tiny red dots. Their light has been traveling 13.3 billion years. Those galaxies likely are small and just forming their first batches of stars. They might eventually merge to become larger galaxies later. We are seeing them in embryonic form. At slightly higher redshifts, 15 or 20, any stars or clusters might be even younger. Possibly we're talking about the first sizable star clusters forming, each perhaps too faint individually for us to see without extreme lensing help. Eventually, as we near redshift 1000, we hit the surface of last scattering. Before that, the universe was opaque plasma, so no direct photons can come to us from earlier times. Except neutrinos or gravitational waves potentially, but that's another story. So we have a cosmic photo album that starts around the birth of visible galaxies and continues to the present. What lies beyond our observable universe? Likely more of the same cosmic web, galaxies and voids extending indefinitely, or at least to some huge extent. But that region is forever inaccessible to us due to the finite speed of light and cosmic expansion. In a sense, those unobservable galaxies are like ghosts, real, but we will never see their light. It's strange to think that the universe could be vastly larger than what we can observe, containing countless galaxies forever beyond our horizon. However, within our horizon, we have what appears to be a fair sample of the universe's contents. The distribution of galaxies and their properties seem uniform on large scales. The cosmological principle, no special spot. so likely the observable portion is representative of the whole. We can, with some confidence, generalize that galaxies exist everywhere in similar ways. As time marches on, the edge of our observable universe moves outward. We catch light from slightly more distant regions. But concurrently, due to accelerated expansion, distant galaxies are moving away faster and faster. Eventually, there's a limit. Distant galaxies' light gets redshifted into oblivion or never reaches us if space expands too swiftly. In fact, billions of years in the future, an observer in our Milky Way, or its merged descendant, will see fewer and fewer external galaxies. Far-off galaxies will slip beyond detectability. Closer ones will eventually follow. Trillions of years hence, perhaps only the local group's merged remnant will be visible to its inhabitants. All other galaxies' light will have stretched beyond recognition or dropped below detectable levels. The universe will seem to them an empty, dark void with one galaxy, a very different cosmic vista than the rich one we enjoy now. But that far destiny is far beyond our concern. At present, we stand at a time when the universe's story is richly accessible. We can look back almost to the beginning and see evidence of those earliest chapters. We see the whole sweep, from primordial galaxies just lighting up, through the turbulent adolescent universe of quasars and starbursts, to the settled modern universe of grand spirals and ellipticals, and even hints of the quiet senescence to come in some galaxies. Galaxies also change internally over time. They age. We have already touched on this. Star formation slows as gas runs out. Stellar populations shift toward older, redder stars. An active blue spiral can become a passive red lenticular or elliptical. The universe's population of galaxies is undergoing an overall aging. The cosmic star formation rate today is about an order of magnitude lower than it was 10 billion years ago. Many galaxies that once were lively are now quiescent. We observe this directly. In clusters at moderate distances, a few billion years ago, we see more spirals and irregulars than in nearby clusters, where most galaxies are ellipticals/lenticulars. In the field, we see that the fraction of star-forming galaxies was higher in the past. The transformation mechanisms, mergers, environment, internal exhaustion, have gradually quenched many galaxies. An aged galaxy, like a massive elliptical in Virgo, is essentially a memorial to its youthful past. Its light is now mostly from low-mass, long-lived stars, orange K-giants, red dwarfs, etc. The O and B stars that once made it blue are gone. They lived short lives long ago. Without new stars, the galaxy has slowly reddened. In a sense, galaxies have colors akin to leaves. A bright star-forming galaxy is like a green leaf full of chlorophyll, young, vigorous, while a quenched galaxy is like an autumn leaf that's turned red-brown. The green, blue light of young stars is gone, leaving the oranges and reds of the older population. Some galaxies can be rejuvenated if they get new gas. For instance, a previously quenched lenticular might accrete gas from a companion or the intergalactic medium and reignite some star formation. But generally, once a galaxy becomes a large elliptical, it doesn't return to a spiral. Too much structural change and gas loss has occurred. Rejuvenation usually happens in smaller doses, like a very low level of star formation on top of an old population, often seen in S0 galaxies that have a few patches of star formation from some residual or acquired gas. As eons pass, galaxies will continue to fade. One can extrapolate, in about 100 billion years, with no major external influences, the Milky Way, if it hadn't merged with Andromeda, hypothetically, would use up much of its gas and form mostly red dwarfs. The bright blue stars it has now will be long gone. Even the Sun will be a white dwarf by then. The galaxy's luminosity would decline. Low-mass stars can burn for extremely long times, trillions of years for the smallest red dwarfs, so the galaxy would never go completely dark in the foreseeable future.
but it would become very faint and mainly infrared, since red dwarfs emit in red IR. Planets and remnants might still orbit quietly, but the grand star formation nebulae and massive clusters would be distant memories. A truly old galaxy would be a sparse collection of slow-burning embers. Imagine, trillions of years hence, a lone red dwarf civilization looking out at a night sky where maybe only red and orange stars speckle the heavens and no Milky Way band, because the bright contributors to it have died out. That's a far extrapolation, but it is where aging leads. However, interactions can reset the clock for some galaxies. The Milky Way, for example, will merge with Andromeda and likely spark a wave of new star formation as gas clouds slam together, thus temporarily making a new blue generation of stars before settling down to red retirement. So galaxies can have multiple epochs of youth in a way, e.g., after a quiet period, a merger can make them briefly young again in terms of star content. These cycles complicate a straightforward age narrative, but overall, as the universe's expansion dilutes fresh infall and as available unmerged galaxies dwindle, rejuvenations will become rarer. Eventually, most star formation will wind down everywhere. In the present, we still see a mixture. Some galaxies are in their vigorous star-forming phase, especially many smaller ones and some big ones like grand design spirals. Others have already quieted down. This mix is part of the so-called galaxy bimodality. The cosmic population tends to split into blue star-forming galaxies and red quiescent galaxies, with fewer in between. This tells us that the transition, blue to red, can be relatively rapid on cosmic timescales, a few 100 million years perhaps to quench a galaxy via a merger or other means. Thus, a galaxy might spend a few billion years actively forming stars, then, after a quenching event, fade to red and spend tens of billions of years in that state. While galaxies change, the universe around them changes too. Expansion continues, and the balance between gravity and expansion determines whether structures grow or not. Currently, we are in a phase where expansion wins on the largest scales, so the cosmic web is sort of frozen beyond supercluster scales, and within those scales, gravity still slowly merges galaxies within bound groups/clusters. In the far future, each bound group or cluster will merge into one huge galaxy. So ironically, while individual galaxies fade, the average galaxy's mass may actually increase due to mergers, but those will be the last major ones. Now, shifting from physical changes to a more speculative realm, consider the possibility of life in other galaxies. As we look at the myriad galaxies, we cannot help but wonder, is there life out there? And if so, how abundant is it? We know life arose in one galaxy, our own, at least on one planet. Given the vast number of galaxies and stars, it seems statistically inevitable that many galaxies harbor life-bearing worlds. Each galaxy contains billions of stars and likely billions of planets. Even if only a small fraction of stars have habitable zone planets, the sheer numbers mean potentially millions of such planets per galaxy. And with billions of galaxies, well, the number of possible abodes for life becomes astronomical indeed. We, beings made of heavy elements, are direct products of our Milky Way's star formation and chemical evolution. The same processes have occurred in every galaxy. So the ingredients for life, carbon, water, energy sources, should be widespread. Life might have arisen independently in countless locales. It could be microbial, or it could, on some worlds, evolve complexity and intelligence. When we gaze at Andromeda, that large spiral many like to photograph, we are looking at possibly 1 trillion stars and perhaps several trillion planets. It would be the height of arrogance to assume none of those trillion stars hosts a living world. Perhaps on a planet orbiting a sun-like star in Andromeda's disk, beings gaze back at the Milky Way as a faint blur and have similar wonder about us. Yet, the distances are so vast,
2.5 million light-years between us and Andromeda, that any exchange of information is exceedingly unlikely, barring some science fiction-level technology. For all practical purposes, any life in other galaxies is isolated from us by enormous gulfs of space and time. Still, the idea that the universe could be teeming with life, consciousness, and even civilizations scattered among the galaxies is awe-inspiring. It transforms those faint smudges of light into potential distant homes. We have essentially no way at present to detect life in other galaxies. We can't resolve individual planets or even individual stars in most galaxies beyond our local group, except via special cases like gravitational microlensing events. But we can reason. The physical laws are the same everywhere. Chemistry is universal. There's nothing special about the Milky Way that would make it uniquely favorable to life. In fact, some researchers consider that large, active star-forming galaxies might occasionally have more hazardous environments, more supernovae, etc., whereas a quieter galaxy might be more benign. But life on Earth has endured supernovae and cosmic rays, so perhaps these are not strict barriers. One interesting point: galaxies with different histories might have different proportions of heavy elements, which could affect planet formation. Very metal-poor galaxies, like some dwarfs, might have fewer solid planets because heavy elements form the cores of terrestrial planets. The early universe's galaxies likely had only gas giants, if any planets at all, until first generations of stars produced enough metals. Now, in the modern universe, most large galaxies have enough metals for abundant rocky planets. So life's probability might have increased over time as the universe became more enriched. That suggests the universe may be more life-friendly now, at age 13.8 billion years, than it was at, say, age 2 billion years, simply because more chemical raw materials for life, like phosphorus, which comes from stars, or oxygen for water, etc., are available and planets are more common. If life is widespread, what does it mean for the cosmos? It means the universe has, in a sense, a way to know itself in many places. We on Earth are one small voice, but imagine countless others in distant galaxies, each observing their sky, maybe developing science, maybe sending out signals that will never reach another galaxy because of distance, but still, they exist. The universe could be filled with such points of light, intellectual light, one might say, each unaware of the others because of the enormous separations. It's a bit poignant. The universe could be bursting with life and intelligence, yet each island galaxy is mostly isolated, separated by oceans of space that likely cannot be crossed with communication or travel given known physics. It's as if each galaxy is its own closed ecosystem of life. If that's the case, then our efforts to find extraterrestrial intelligence might only succeed within our own galaxy, listening for signals, or perhaps one day sending probes to nearby stars. Contact with any intelligence in another galaxy is far beyond any realistic scenario. Signals would take millions of years, even if they were intentionally directed, which they likely wouldn't be, as there's no way for them to know we're here. So in practice, each galaxy's life forms must live out their existence without knowing for sure if they are alone in their galaxy, and certainly without direct contact with other galaxies' life forms. Nonetheless, just knowing that life likely exists out there can change our perspective. We can look at a galaxy cluster and imagine it may host billions of biospheres. It adds emotional depth to those points of light. It also humbles us. We are one tiny form of life on one planet, around one star out of 100 billion in one galaxy among billions. It's the ultimate Copernican extension. Not only is Earth not the center of the universe, our galaxy isn't either, and life, if common, is not centered on us. And if, by some chance, life is extremely rare, if it turns out Earth is one of very few cradles of life, then the burden on us is immense. We carry the flame of consciousness for the cosmos, perhaps a flame that flickers only in a few places. That would make the universe a lonelier place, and our role all the more significant, to cherish and propagate life and consciousness. Either way, the mere possibility of life throughout the galaxies casts the cosmos in a new light, a possibly living cosmos, or at least a cosmos with many oases of life. After contemplating these sweeping themes, the birth and death of galaxies, the rise of stars and possible life, we return to the personal perspective. We live inside a galaxy. What does that mean? It means when we look up at the night sky, we are looking through the lens of our galaxy's stars. All the starry sky we see is part of the Milky Way, except a few smudges, like Andromeda. It means the story of the Milky Way is our story.
For a long time, humanity didn't know that those spiral nebulae out there were other galaxies. Only in the 1920s did Edwin Hubble and others prove that the Andromeda Nebula was far outside the Milky Way, settling the great debate and expanding our known universe enormously. Since then, our perspective has changed from thinking the Milky Way was essentially the universe to realizing it's one of countless universes within the universe. This awareness that we inhabit a galaxy among many is one of the profound intellectual revolutions of the 20th century.
So, to live inside a galaxy is to know that the universe is much larger than our home. The Milky Way is immense on a human scale. 100,000 light-years is far beyond direct comprehension. Yet we know now it's just one disk among billions strewn through space. That can make one feel small, but also connected to a grander existence. We know our galaxy's place in the cosmic web, on the outskirts of Laniakea supercluster. We know its future, merger with Andromeda, eventual fade-out. We've pieced together its past, formation from smaller pieces, multiple bursts of star formation, perhaps a barred spiral structure forming later on. Thus, we have context for our own existence. We're not adrift without a cosmic address. We can say we reside in the solar system, which orbits in the Orion arm of the Milky Way, which along with Andromeda and others forms the local group, on a filament at the edge of the Virgo supercluster. When the cosmos is remembering itself, part of that memory is our emergent understanding of our coordinates in space and time. We've learned that heavy elements in our bodies were forged in the Milky Way's previous generations of stars. Effectively, we are children of the Milky Way. In a poetic sense, the galaxy made us, and now through our eyes and minds, it has become aware of itself. We often speak of, we are the universe experiencing itself. At a more localized level, we are the Milky Way experiencing itself. Tiny, conscious bits of the galaxy that can contemplate the whole. This perspective can instill a sense of belonging and unity. All humans are literally of one dust, cosmic dust from our galaxy's past stars. The light of the sun that sustains us is a typical star's light in the Milky Way. The constellations that our ancestors named are patterns drawn on the backdrop of our galaxy's disk and halo. Our fate, as beings and as a planet, is tied to the galaxy's fate. If, say, a supernova goes off close by, or the galaxy's nucleus had a dangerous flare, it could affect Earth's biosphere. Conversely, what we do on Earth has negligible effect on the galaxy at large. We're too small. Except perhaps one day, life from Earth might spread to other star systems, and thus the galaxy would have a new phenomenon. Interstellar life, a kind of galactic ecosystem spanning multiple stars, originated by us. That remains science fiction for now, but in principle, a galaxy hosting a spacefaring civilization might see life expanding within it, in a way seeding parts of itself with purpose.
To live inside a galaxy also encourages a cosmic perspective that can be spiritually significant to many. When we see pictures of billions of galaxies and realize each is full of wonders, it can make everyday problems feel smaller and inspire a sense of unity with the cosmos. Many astronauts report a profound shift in consciousness the overview effect, when seeing Earth from space, a fragile ball in the vastness. Multiply that to seeing the Milky Way from an outside vantage, which we can only simulate in our minds. One would see our galaxy as a spiral among others, and Earth an invisible speck. This could foster a deep sense of the preciousness of our world and the absurdity of human divisions. We are all riding this great galactic spiral together. In a very literal sense, our lives are bounded by the galaxy. The night sky's beauty, that milky band, is a constant reminder of the greater structure we belong to. We can't easily travel outside the galaxy. It would take an unrealistically long time with current or foreseeable technology to reach intergalactic space, so we will likely remain an intragalactic species for eons, if not forever. Our voyages will be between stars, not between galaxies, unless some exotic breakthrough in physics occurs. But that's fine. The Milky Way has plenty to offer. Think of the diversity within one galaxy. We have regions densely packed with stars, like globular clusters where skies are awash with starlight. Regions almost empty, like the far outskirts where a star's nearest neighbor might be tens of light years away, a dark, lonely void. We have neutron stars, black holes, planets, comets, nebulae, bright blue giants, tiny red dwarfs, an entire zoo of cosmic objects, all bound by the common gravity of our galaxy. We have the relics of ancient history, old stars with virtually no metals, nearly as old as the universe, and the promise of the future, protostars in dusty cocoons that will light up soon. We have cataclysms, supernovae occasionally lighting up. The last seen in our galaxy was over 400 years ago, but surely more have occurred hidden by dust or on the far side. And we have gentle stability. Our sun has been shining steadily for billions of years in a fairly calm part of the galaxy. When we consider everything, to live inside a galaxy is perhaps the most profound scientific realization we have. It situates us in the vastness. It invites us to think on scales far beyond the human, and yet to marvel that our minds can do so. We have used mathematics and physics, products of human thought, to decipher the workings of the entire galaxy we live in and beyond. In doing so, we, who emerged from this galaxy's stardust, have closed a loop. The galaxy has given rise to beings who can, in a way, know the galaxy. Now our journey nears its end. We have traversed from the darkness before galaxies to the emergence of the first islands of light. We examined the anatomy of galaxies, their varieties and inner workings. We followed their life cycles and large-scale patterns. We pondered the interplay of stars and black holes, the webs that bind them, the winds that carry their essence outward. We imagined the presence of life within them and our own place on one tiny world, circling one average star in the Milky Way. It has been a vast journey, outward and inward at once. Let us end with a moment of cosmic contemplation. Envision our Milky Way as seen from a distance. Say, from a vantage point far above the galactic plane, a few 100,000 light years out. You see the great spiral suspended in blackness. Its disk is a gauzy whirl of blue and white, mottled with darker lanes. The central bulge is a warm golden glow. Encircling it all is a dim halo studded with globular cluster sparkles. Perhaps you see the Magellanic Clouds nearby, small smudges orbiting their parent galaxy. Beyond, a spray of other galaxies, the members of the local group, dot the void. Now imagine you are the galaxy, not seen from outside, but feeling from within. The combined gravity of billions of stars, gas clouds, and dark matter holds you together. You feel the slow rotation, 100 million years per turn, like the heartbeat of a cosmic being. You remember when you were younger and gas-richer, and bursts of stars lit up your arms. You foresee a time when you'll be blended with Andromeda into a new form. But right now, you simply exist in a steady state, stars forming at a modest rate, stars dying occasionally in gentle or dramatic ways, a vast collection of worlds and wonders within. Around you, the universe expands.
But you and your local neighbors are bound in your dance. Time flows. Eons pass, though you measure time in rotations and orbits, not in human years. You have no mind of your own to comprehend all this, but a part of you on a certain small rocky planet has developed curious, self-aware creatures who are collectively reaching out with their intellect to understand the totality of what you are. Through them, through us, you, the galaxy, have attained a voice and a consciousness that can describe you. In a poetic sense, we are the Milky Way gazing upon itself with wonder. One galaxy, still turning in the void, carrying at least one species that can reflect on what it means. Multiply that by billions for all the other galaxies, and we sense a cosmos, perhaps filled with meaning, or at least ripe for it. The void is not empty. It is the stage on which galaxies spin and shine, each a cosmos unto itself. And so we leave our narrative with an image, a lone spiral galaxy drifting in silent darkness. It doesn't know we're here, but we know it is here. We, the cosmos contemplating itself, feel a sense of reverence. The galaxy's stars continue to orbit lazily. A cloud of gas collapses somewhere into new suns. A distant cluster in the halo slowly moves along its path. The central black hole waits quietly for its next meal. The galaxy in that image is our own, the Milky Way, viewed from an impossible perspective, a grand pinwheel of starlight and mystery. Everything we have ever known, every person, every tree, every ocean, every mountain, is part of that faint glow. That galaxy is our home, and one day, far in the future, all that will remain of us is maybe a slight alteration in one of its stars, or the whisper of a radio wave traveling outwards. But the galaxy will continue turning long after we're gone, carrying the legacy of all who lived within it, in the changed chemical makeup of its gas, in the artifacts left on some planets, or simply in the fact that for a brief moment, one of its countless stars harbored thinking beings who marveled at the sky. The camera of our mind's eye pulls back further, and now the Milky Way is just one of many fuzzy spirals in a cluster. Further back, the cluster is just one cluster among many against the cosmic web lattice. But let's stop there. Let's focus again on our galaxy, one galaxy, still turning in the void, serene and majestic. The light from its stars takes tens of thousands of years to cross from one end to the other. The faint glow extends outward, fading into the black of intergalactic space. It rotates imperceptibly slowly. To our brief lives, it appears almost eternal and unchanging. Yet we know it is dynamic and alive with cosmic processes. In the quiet of the cosmic night, our Milky Way continues its stately rotation. We, tiny sentient flecks on a minor world inside it, can close our eyes and feel at one with this great wheel of stars. In our hearts, we carry its story, from darkness to light, from simplicity to complexity. A story written in the language of starlight across the vault of heaven. As the galaxy turns, we find meaning not in being central or significant in size, for we are neither, but in understanding and appreciating the beauty and grandeur that surrounds us. This is our galaxy, our home, one of billions, yes, but uniquely ours at this place and time. It drifts through the cosmic night, still illuminated by the myriad fires within, still creating new light. A part of the cosmos that once was dark has become light and aware. And as we conclude our long journey, we can step outside under the real night sky. The Milky Way arcs above, for those fortunate to have dark skies, a spectral veil of our galaxy seen from within. Every point of that veil is a star, many perhaps with planets, some maybe with life. We stand here, consciousness emerged from a collection of cosmic particles, looking up and out. We feel the whisper of the galaxy's ancient memory in that band of light, and we whisper back our understanding into the silence. In that exchange, the galaxy's light entering our eyes and our minds decoding its story. The cosmos remembers itself. We close with that image of the great spiral, turning silently, carrying the echoes of its formation and the faint songs of whatever lives it has fostered. One galaxy, among countless others, continuing its journey through the dark. A wheel of fortune, a wheel of stars, forever spinning, forever moving, and in its own way, perhaps, forever knowing, through the living beings that arise and gaze out from within. The lights dim on our narrative, but overhead the stars of the Milky Way still shine. The story of the galaxies goes on, and we have been part of it. We are part of it, forever connected to the universe that made us. The spiral turns in the cosmic night, and we turn with it, children of the galaxies, awake and full of wonder.